Right now, light that left a galaxy nearly 12 billion years ago is passing through the room you're lying in. You're listening to Space Before Sleep. Before we begin, take a moment to get comfortable. Maybe you're already lying down, maybe you're sitting somewhere quiet, or maybe this video is playing softly while you wind down after a long day. However you've arrived, you're in the right place. Space Before Sleep is all about exploring big ideas in a calm and gentle way. No rush, no pressure to keep up with every detail. Just a slow journey through science, curiosity, and the universe, designed to help your mind relax while it learns something new. Tonight, we're going to explore a discovery that sounds simple at first, a photograph of a galaxy. Now, if you've never heard of the Big Wheel before, that's completely okay. It was only found in 2024, and it's not something that usually comes up in everyday conversation. But once you learn about it, it quickly becomes one of those things that quietly reshapes the way you think about the universe. Because the Big Wheel isn't just a galaxy, it's not just a large galaxy, it's a fully formed spiral, with the same graceful shape our own galaxy wears tonight, sitting at a moment in cosmic history when nothing like it was supposed to exist. And when scientists try to explain how it got there, they run into a strange problem. By every rule they trusted, there simply wasn't enough time. It was found almost by accident. In an office in Pasadena, California, an astronomer named Charles Steidl was studying the light of a distant quasar, and there, in the corner of the image, sat a wheel, 11,700,000,000 light-years away, existing when the universe was barely 2 billion years old, already 5 times the mass of the galaxy you are lying inside right now. Nobody was looking for it. Nobody expected it. And the scientists who confirmed it call it, in their own words, a complete mystery. That's what we're going to explore together tonight. Not quickly, not with complicated math or technical language. Instead, we'll move slowly, step by step, building a picture of what a spiral galaxy really is, why it takes so long to build, how this one was found, and why its shape is forcing astronomers to rewrite the timeline of the early universe. But before we dive into the deep end of cosmic history, let me ask you something simple. Where are you listening from tonight? Maybe you're at home, somewhere quiet. Maybe the lights are already off. Perhaps you're curled up under a blanket, or maybe this video is playing softly on a phone beside your bed. Wherever you are in the world, it's interesting to remember that while you're listening to this, the universe above you is quietly continuing its vast and complicated story. Stars are forming, galaxies are drifting through space, and far beyond the reach of any telescope you could look through with your own eyes, the big wheel is still turning, doing what galaxies do, gathering stars, holding its shape, and carrying on without any need for us to watch. If you feel like sharing, you can always leave a comment about where you're listening from. It's always nice to see how far these quiet space journeys travel around the world. And if you find these kinds of slow explorations soothing, you can also like the video and subscribe to the channel. That helps more people discover Space Before Sleep, and it allows us to keep making calm space stories like this one. Let us begin. Step into the impossible. Somewhere inside an image taken by a space telescope, there sits a galaxy that breaks the rules of its own age. It has arms. It has a smooth, curling shape, the same kind of shape our home galaxy wears today. And it existed back when the universe itself was still young enough to be called a child. For decades, astronomers trusted a simple rule. Young galaxies should look rough. They should look broken, lumpy, and unfinished, like a construction site rather than a finished building. That rule stayed grounded in real observations and real physics, checked and rechecked for years. It held up so well that almost nobody thought to question it. Then, a fully built spiral galaxy showed up in the wrong chapter of cosmic history. This is confirmed by direct observation, not speculation. Astronomers measured its light, tracked its motion, and confirmed how far back in time it sits. There was no error hiding in the data. The galaxy was exactly where it should not be, spinning calmly in an era that was supposed to be pure chaos. Researchers nicknamed it the Big Wheel, and the name fits perfectly. Picture a giant spinning wheel made of stars and glowing gas, arms curling outward in a slow, graceful sweep from its center. Now picture that wheel fully built at a point in time when, according to nearly every major model, galaxies were still supposed to be scattered rubble, still crashing into each other, still years away from anything this tidy. Here is a number worth sitting with. This galaxy appears to hold roughly 5 times as many stars, in terms of mass, as our own galaxy does today, and it reached that size at a moment when the universe had barely started keeping score. That detail alone reshapes the story. This is a galaxy that seems to have skipped several steps in its own life journey, arriving fully formed ahead of schedule. None of this rests on a single blurry image or a rushed announcement. The result went through the normal process of scientific review, published for other astronomers to check, question, and try to break before anyone accepted it. That makes this confirmed observation, standing on solid ground rather than a hunch dressed up as a headline. The open mystery sitting underneath it all is simple to state and hard to answer. How did nature manage to build something this organized, this early, this fast? Every galaxy carries a kind of story written into its shape, and most early galaxies were expected to tell a rough, unfinished one, still finding its footing. The Big Wheel tells a very different story, one where the ending seems to arrive far too soon in the book. That mismatch alone pulled astronomers into a debate that is still running right now, with no final answer settled yet. This single discovery forces a hard question that will not let go. If one galaxy could grow up and organize itself this fast, how many others did the same thing, unseen and unnamed, scattered across corners of the sky nobody has pointed a telescope at yet? The rest of this story follows that question all the way down, starting with something simpler than it sounds. What a spiral shape actually requires in the first place, and why building one this early might be one of the strangest puzzles in modern astronomy. Before we can understand why the Big Wheel breaks the timeline, we need to understand what a spiral even is, and why it is such a fragile, hard-won shape for a galaxy to wear. Not every galaxy gets to look like a pinwheel. Most of the earliest structures in the universe look nothing like one, and that difference turns out to matter more than most people realize. Galaxies come in a handful of basic shapes. Some are round or oval blobs, packed with stars moving in random, tangled directions with no shared path. These are called elliptical galaxies, and their stars often formed long ago in a rush of violence, then settled into a jumble with no clear pattern. Other galaxies barely have a shape at all. They look stretched, patchy, or broken, and astronomers simply call them irregular. Astronomers have sorted galaxies into these rough families for a very long time, comparing thousands of nearby examples to build a reliable picture of what each shape usually signals about a galaxy's past. Round, jumbled ellipticals tend to carry a violent history behind them. Patchy, broken irregulars usually mean a system still under construction. Smooth, spinning spirals sit at the far end of that scale, the shape astronomers associate with age, calm, and time. A spiral galaxy takes far more coordination to build than either of those other shapes. Picture a flat, thin disk spinning together like a record on a turntable. Almost every star in that disk orbits the center in roughly the same direction, on roughly the same flat plane. Within that spinning disk, bright lanes of stars and glowing gas trace out curling arms, winding outward from the center in graceful, sweeping curves. This is the part that matters most. A spiral shape is not just decoration, it is a signature of order. It tells you the stars and gas inside that galaxy are not moving randomly. They are moving together, in step, following a shared rhythm around a shared center. Our own galaxy wears this same shape, a flat spinning disk with arms of its own, home to our star and everything we know. Building that kind of order takes time and calm. Gas has to cool down from a hot, turbulent state into something smooth and settled. It has to sink into a thin, flat layer instead of swirling around in every direction at once. Only after that settling happens can the graceful curve of a spiral arm appear at all. Skip the settling, and a galaxy stays a clump, or a smear, or a shapeless haze. It never becomes a wheel. That is why finding a fully formed spiral so early in cosmic history is such a big deal. It is not simply an old galaxy. It is a galaxy that already learned how to move in step, arm over arm, at an age when it was barely supposed to have learned how to hold itself together at all. Astronomers can even measure how tightly a spiral holds its shape, tracking the arms across an entire disk to confirm they are not just a random pattern of bright clumps lining up by chance. Real spiral arms follow a smooth, predictable curve from center to edge, repeating in a way pure randomness never produces on its own. That level of geometric consistency is part of what convinced researchers this ancient galaxy deserved the same label given to spirals sitting much closer to home. So, if spiral shape requires calm, and calm normally takes ages to arrive, how did anyone expect galaxies to look at all in the universe's first billion years? That question brings us straight to the growth chart astronomers built, piece by piece, to answer exactly that. Every field of science eventually builds a timeline, a rough sketch of how something is supposed to grow from nothing into something whole. Galaxy formation has one too, and for a long time it looked solid. The story starts right after the beginning of everything, when the universe was an almost perfectly smooth, thin haze of gas, with only the faintest ripples of extra density scattered through it. This part is strongly supported theory, built on decades of measurements of the oldest light in the universe. Those tiny ripples mattered enormously, because gravity always favors the crowded spot. Regions with slightly more material pulled in more material, slowly, patiently, over enormous stretches of time. From those ripples, small clumps of matter began to form first, mostly invisible dark matter, with ordinary gas following along behind, drawn in by gravity. Inside those first clumps, the earliest tiny galaxies lit up, dim and small compared to anything we would recognize today. This is the accepted starting chapter of the standard growth model, and observations of the ancient universe back it up well. From there, the model says galaxies grow the same way a snowball grows rolling downhill. They collide, they merge. Small galaxies crash into other small galaxies, sticking together, growing heavier and larger with every impact. Repeat that process across hundreds of millions of years, and eventually you get galaxies with real size, real mass, and enough stars to matter. According to this growth chart, order comes last, not first. A galaxy is expected to spend a long, rough childhood absorbing collisions before it ever settles into anything as delicate as a spinning disk. Only after the crashing slows down, once a galaxy stops getting hit every few 100 million years, can its gas finally cool, settle, and arrange itself into the kind of calm structure a spiral arm needs. This chart is not some fringe idea cooked up by a handful of scientists chasing headlines. It comes from massive computer simulations that track billions of particles of matter across the full history of the universe, tuned to match everything astronomers already know about how galaxies behave nearby. Those simulations have explained an enormous amount, from the way galaxies cluster together to the way our own galaxy likely grew over time. That track record is exactly why nobody expected this particular chart to fail so publicly. Under this model, building something like the Big Wheel should have taken roughly half the universe's entire lifespan, maybe more. Scientists were not guessing wildly when they expected the early universe to look like a demolition site. They were following a chart built from real physics and real prior observations, one that had explained the galaxies we already knew reasonably well. That is exactly why a fully organized spiral, spotted at a fraction of that expected age, hit the field so hard. The chart said one thing, the sky said another. And to understand just how contradictory that is, we need to look closer at what the young universe was actually supposed to feel like from the inside, a place scientists expected to be anything but calm. Space in the young universe was a crowded place, and that crowding was supposed to make peace nearly impossible. Right after the beginning, everything sat much closer together than it does now, because the universe had not yet stretched itself out through cosmic expansion. Galaxies formed in dense neighborhoods, packed shoulder to shoulder compared to the wide open spaces galaxies enjoy today. Crowded neighborhoods mean frequent encounters, and frequent encounters mean frequent collisions. Earlier space telescopes seem to confirm exactly that picture. Looking back toward the early universe, older observations showed galaxy after galaxy with broken, patchy, asymmetric shapes, exactly what a demolition derby should leave behind. Bright clumps of newborn stars scattered unevenly across a smeared, irregular body, nothing like the smooth, symmetrical wheel of a mature spiral. This evidence was real, and it lined up neatly with the growth chart from the last chapter. Here is why collisions are so damaging to order specifically. When two galaxies merge, gravity does not politely blend their stars together, it flings them. Stars that were once calmly orbiting in a flat plane get kicked into wild, tilted, random paths, like a game of pool where every ball scatters after the break. A disk that took a long time to settle can get scrambled again in a single violent pass, undoing the calm it had only just achieved. Because of this, the leading theory held that spiral disks needed a long, quiet stretch of time without major collisions to survive at all. Early on, with galaxies packed close and merging often, that quiet stretch simply should not have existed yet. A newborn spiral shape, if one somehow appeared, was expected to get wrecked again almost immediately, undone before it ever had a real chance to last. Put plainly, the model predicted a universe where roughly 9 out of every 10 young galaxies should look messy, clumpy, or broken, not neat and spiral. That number was not an arbitrary guess. It came from simulations that tracked how often galaxies of a given size were expected to collide during the universe's first couple of billion years. This prediction did not come from one lone study either. Multiple independent research groups, running different simulations with different starting assumptions, kept landing on roughly the same result. Young galaxies should stay rough and unsettled for a long stretch of cosmic time, sometimes lasting several billion years, before conditions calmed down enough for a proper disk to survive intact. That kind of agreement across separate teams is usually a strong sign a model is on solid footing. There was good reason to trust that picture, too. Earlier observations of galaxies from roughly this same era genuinely did look messy, more often than not, patchy and asymmetric in exactly the way the demolition derby model predicted. That earlier evidence was not wrong. It simply was not the whole picture, and nobody yet knew how much was still hiding just beyond what older telescopes could resolve. So when astronomers pointed a brand new, far more powerful telescope at that same early era, they expected to see confirmation of the chaos. What they actually found would end up quietly rewriting a piece of the story. But first, that discovery required a telescope built specifically to look further back and colder and clearer than anything that came before it. No instrument built before it could see what this one was designed to find. The James Webb Space Telescope orbits far from our planet, roughly 1 million miles out, parked in a spot where light from our star, heat from our planet, and its own instruments can all stay balanced and controlled. Cold matters enormously here, because the telescope was built to detect infrared light, a kind of light invisible to human eyes but essential for peering into the deep past. Light from extremely distant galaxies gets stretched on its long journey across an expanding universe. Visible light, leaving an ancient galaxy, gradually shifts into infrared by the time it reaches us, stretched out by the steady expansion of space itself, during the billions of years that light spends traveling. Earlier telescopes, tuned mostly to visible light, simply could not catch much of this stretched, faded signal. This telescope was purpose-built to catch exactly that kind of light, and to catch it in extraordinary detail. That combination, a huge mirror spanning roughly 21 feet across, paired with extremely sensitive infrared detectors, lets this telescope see fainter, older, and more distant objects than any observatory before it. It can resolve fine detail in galaxies that once appeared as nothing more than a formless smudge. Structures, shapes, and even the internal motion of gas inside impossibly distant systems suddenly became visible for the first time. This upgrade in seeing power is confirmed engineering and confirmed results, demonstrated across thousands of published observations already. It is the reason a galaxy like the Big Wheel could even be identified as a spiral at all, rather than just another blurry dot lost in the noise. Earlier instruments might have caught its light. They almost certainly could not have shown its shape. Think of it like finally getting reading glasses after squinting at a distant sign for years. The sign was always there. The words were always printed on it. You simply lacked the tool needed to resolve the details clearly enough to read them. The mirror itself is built from 18 hexagonal gold-coated segments, folded up for launch and unfolded once safely in space, working together as a single smooth surface. Every one of those segments has to line up with astonishing precision, far tighter than the width of a human hair, or the whole image blurs. Getting that alignment right, and keeping the entire structure cold enough to avoid drowning faint starlight in its own heat, ranks among the hardest engineering feats ever pulled off for a scientific instrument. A tennis court-sized heat shield trails beneath the telescope, blocking stray warmth and light, so the instruments above can stay near -400 degrees Fahrenheit, cold enough for the faintest infrared glow from the ancient universe to actually register above the telescope's own background noise. Without that extreme cold, ancient light this faint would simply vanish into static, and a galaxy like the Big Wheel would have stayed invisible. With this telescope's power established, the stage is set for how the Big Wheel actually turned up. It was not found through a careful, targeted search aimed specifically at spiral shapes in the ancient universe. It showed up almost by accident, hiding in the glare of something else entirely, waiting for someone to notice it. Some of the biggest discoveries in astronomy happen while scientists are looking for something completely different, and this was exactly that kind of moment. A quasar is an extremely bright, distant object powered by a massive black hole feeding on surrounding gas, blazing with more light than an entire ordinary galaxy combined. Astronomers were pointing this telescope's instruments at one particular quasar, using its brilliant light as a kind of cosmic flashlight to study material sitting between it and us. Quasars make excellent tools for this kind of study, because their intense light shines straight through foreground gas and dust, revealing details along the way. While studying that light, researchers noticed something odd sitting nearby in the same field of view. It had structure. It had a shape that looked strangely familiar, curling arms, a flattened disk, details typically associated with much closer, much younger galaxies. The first instinct among the team was skepticism rather than excitement. The lead researcher initially assumed this object was simply an interloper, a much closer, more ordinary spiral galaxy that happened to sit in the same direction as the quasar by pure coincidence, unrelated to the ancient light being studied. That would have been the boring, expected explanation, and boring explanations are usually correct. Then the team measured its distance properly, using the stretch in its light to calculate exactly how far away it truly sat. The boring explanation collapsed immediately under real numbers. What the data actually revealed was a galaxy sitting almost as far back in time as the quasar itself, genuinely ancient, caught by pure luck in the same tiny patch of sky. Confirmed distance measurements do not leave much room for doubt once cross-checked, and this one was checked carefully before anyone announced anything publicly. The galaxy was real, its age was real, and its shape was unmistakably a spiral. A discovery this significant, hiding accidentally behind an unrelated target, says something important about how much more might still be sitting unnoticed in existing data, waiting for the right person to glance in the right direction. This kind of accidental find happens more often in astronomy than most people expect. Archives fill up with observations aimed at one specific target, while countless other objects sit quietly in the background of the same image, unexamined for years. Some researchers now spend entire careers combing back through old data with fresh eyes, hunting for exactly this kind of overlooked detail. The big wheel is a reminder that the next major discovery might already be sitting in a hard drive somewhere, waiting to be noticed. Skepticism, in this case, turned out to be the right first instinct, and the right instinct is exactly what kept the eventual announcement credible. Extraordinary claims in astronomy get treated with suspicion until the numbers survive every attempt to knock them down, and these numbers survived. Once the team accepted what they were looking at, the next job was naming this thing properly and pinning down exactly how far back in time its light had traveled, numbers strange enough to make even seasoned astronomers pause before publishing them. A nickname stuck to this galaxy almost the moment researchers saw its shape clearly, and the name explains itself. Big Wheel, simple, direct, and accurate. The galaxy's disk, with its curling arms and rounded outline, genuinely resembles a giant wheel spinning slowly through open space. Scientists give nicknames like this to especially striking or important discoveries, partly to make them easier to talk about, and partly because some objects earn a bit of personality once their story becomes clear. This one earned its name honestly. Naming a galaxy is the easy part. Measuring its distance accurately is where the real work happens. Astronomers determine distance for objects this far away by studying how much their light has stretched during its long journey across an expanding universe, a reliable, well-tested method used across the entire field. The more the light has stretched, the further away and further back in time the object sits. This measurement is confirmed physics, not a rough estimate pulled from a guess. Applying that method to the big wheel produced a number that is difficult to hold in your head. The galaxy sits roughly 11,700 million light-years away. A light-year is simply the distance light travels across one full year, moving at the fastest speed anything in the universe is allowed to move. Multiply that speed by 11,700 million years, and you get a gap between us and the big wheel so enormous that ordinary comparisons start to break down. Here is a way to feel that number rather than just read it. Our own planet is roughly 4,500 million years old. The light now arriving from the big wheel left its source long before our planet had even begun to form, before there was anything resembling Earth anywhere in this region of space. That light has been crossing the universe, silently, uninterrupted, for longer than our entire planet has existed. This is exactly why studying extremely distant galaxies works like a kind of time travel. Astronomers are not describing the big wheel as it exists today, because nobody currently knows what it looks like right now. They are describing exactly what it looked like the moment that ancient light left it, frozen in transit ever since. Whatever the big wheel has become since then remains, and will likely always remain, unknown. Every measurement carries some margin of error, and honest scientists always report that margin rather than hiding it. Even accounting for that uncertainty here, the distance to the big wheel is not seriously in dispute. Independent teams, checking the same data, using the same well-established method, keep landing on the same conclusion. This galaxy sits deep in the early universe, full stop, with no reasonable alternative explanation left standing after the numbers were checked. With the name settled and the distance confirmed beyond reasonable doubt, one question becomes unavoidable. Exactly how young was the universe itself at that moment, And just how impossible does a fully built spiral galaxy become once that age gets pinned down precisely? Every distant galaxy carries a kind of birth certificate stamped into its light, and the Big Wheel's certificate reads almost unbelievably early. The light we now receive from the Big Wheel left it about 2 billion years after the beginning of the universe. Compare that to the universe's full current age, roughly 13 billion, 800 million years, and the picture becomes clear. That galaxy had already built itself into a massive, organized spiral by the time the universe had lived through only about 15% of its entire life so far. 15%. Not halfway. Not even a quarter. A sliver near the very start. Try this comparison to feel the weight of that number properly. Imagine compressing the universe's entire life story into a single 100-year human lifetime. Under that scale, the Big Wheel already existed as a fully grown, orderly spiral galaxy by the time that lifetime had barely reached its 15th birthday. Everything else this story has covered so far, mergers, chaos, gradual settling, was supposed to still be playing out through most of that imagined childhood, not finishing early. This detail is what turns an interesting discovery into a genuine scientific problem. Confirmed observation places a fully organized spiral disk at this exact early moment. Leading theory says a disk like that should not have finished assembling for a long stretch of time afterward. Both of those things cannot be fully true at once without something in the picture needing revision. It is worth pausing on what makes this particular slice of time so distinct from the universe we see around us today. Space itself was smaller and denser back then, everything packed closer together, still early in its long process of stretching outward. Studying an object from this era means studying conditions genuinely different from anything nearby telescopes can observe directly, which is exactly why a fully organized structure showing up here carries so much weight. It helps to be precise about what counts as confirmed here and what remains open. The age of the universe itself, roughly 13 billion, 800 million years, is one of the most well-measured numbers in all of science, checked repeatedly through completely independent methods that keep agreeing with each other. The Big Wheel's distance, and therefore its age when its light was emitted, is also confirmed through careful, cross-checked measurement. What remains a genuine open question is simply how a structure this advanced managed to exist at that particular point on the timeline. This particular slice of cosmic history, the first couple of billion years after the beginning, has become one of the most closely studied stretches of time in modern astronomy. It is the era when the very first galaxies were supposed to still be assembling themselves piece by piece, and it is exactly the era this new telescope was built to study in detail. Finding a fully organized spiral parked right in the middle of that era is not a minor footnote. It sits directly inside the window scientists care about most. Some discoveries nudge a scientific model, others threaten to knock a supporting beam out from underneath it entirely. Astronomers are still deciding which category this one belongs to, and the answer depends heavily on details that get stranger the deeper you look, starting with exactly how big and how heavy this early giant actually turned out to be. Mass is the number that turns a strange discovery into a genuinely alarming one, and the Big Wheel's mass is enormous. Astronomers estimate a galaxy's mass by carefully combining several pieces of evidence: how bright it appears across different wavelengths of light, how that brightness is distributed across its structure, and how fast its material is moving under the pull of gravity. None of these methods involve placing anything on a scale, obviously, but together they produce mass estimates that have been tested and refined for decades against galaxies close enough to measure by multiple independent techniques at once. Applied to the Big Wheel, that method points to a galaxy holding roughly 5 times as much mass as our own home galaxy carries today. Our galaxy is not small. It contains hundreds of billions of stars, arranged across a wide, structured disk that took billions of years to build. Multiply that entire structure by 5, and you get a sense of just how much material the big wheel had already gathered and organized. Reaching that kind of mass normally takes an enormous amount of accumulated time. Stars need to form, generation after generation, while gas keeps flowing inward and merging keeps adding fresh material to the pile. The standard growth chart from earlier in this story assumes galaxies build up mass gradually, in fits and starts, stretched out across most of the universe's history. Finding a galaxy this heavy this early suggests some of that assembly happened on a drastically compressed schedule. Mass estimates like this one always carry a margin of error, and responsible researchers report that margin honestly rather than presenting a single number as flawless. Even allowing generously for that uncertainty, the big wheel still comes out several times heavier than our own galaxy. Shrinking the estimate toward the cautious end of its range does not make the underlying puzzle disappear. It only softens the edges slightly. Researchers studying the big wheel have floated an early idea worth marking clearly as theory, not settled fact. Growing this fast may require unusually rich surroundings, a denser than average patch of the early universe supplying extra gas at a faster rate than typical regions could manage. That explanation is plausible. It is not yet proven, and other explanations remain firmly on the table as well. Try translating that mass figure into something closer to a head count. Our home galaxy is thought to hold somewhere in the neighborhood of 200 billion stars, give or take, depending on how many faint, hard-to-count dwarf stars get included in the estimate. Multiply that rough figure by 5, and you land on a population approaching 1 trillion stars, all packed inside a single galaxy that existed when the universe had barely gotten started. That is not a number scientists expected to write down for an object this ancient. Mass alone would already make the big wheel remarkable, but mass by itself does not explain the shape. A galaxy could theoretically gather enormous mass through chaotic, disorganized growth and still end up looking like a formless blob, heavy but shapeless, packed with stars moving every which way. The fact that all that mass ended up arranged into a smooth, symmetrical, spinning disk adds an entirely separate layer to the mystery, one that becomes even stranger once you measure exactly how far that disk actually stretches across the sky. Size is where the big wheel stops sounding merely unusual and starts sounding almost architectural. The disk of the big wheel spans more than 100,000 light-years from edge to edge. Our own galaxy stretches across a similar scale, roughly 100,000 light-years in diameter, a number astronomers consider genuinely large, even among nearby fully mature spirals. The big wheel does not simply match that scale. Measured by total area, it covers roughly twice as much visible territory as our own galaxy does. Diameter and area are not quite the same measurement, and the difference matters here. Diameter tells you how far it is across the galaxy in a straight line. Area tells you how much total surface the disk actually covers, factoring in its full spread from every direction, not just a single line through the middle. A galaxy with twice the area of another is not simply a little bigger. It represents a dramatically larger structure, holding room for a proportionally larger population of stars and gas spread across its disk. Astronomers measure this kind of size using the same distance and light data described earlier in this story, combined with careful geometry accounting for how the disk is tilted relative to our line of sight. A disk viewed edge-on looks like a thin line. The same disk viewed face-on reveals its true, full spread. Getting the true size right requires correcting for that tilt precisely. Another step where careful, peer-reviewed measurement replaces simple guesswork based on a raw image. Building a disk this size requires more than just piling on mass. It requires that mass to spread out smoothly and evenly across an enormous area, without collapsing into disorganized clumps or getting torn apart by outside disturbances. Extending order across a structure this wide, rather than just packing order into a small, dense core, is its own separate achievement, one that adds weight to just how advanced this galaxy already was. A small, tightly packed clump of order is one thing. Stretching that same order across 100,000 light-years of open space is another problem entirely. Consider the scale in more relatable terms. Light itself, the fastest thing in existence, needs over 100,000 years just to cross from one side of this disk to the other. A signal sent from one edge, traveling at the absolute speed limit of the universe, would still take that entire span of time to reach the far side. That is the size of the structure this story is describing, fully organized, fully spinning, sitting at an age when structures this size were expected to still be scattered fragments. Even among the largest, most impressive spiral galaxies sitting near us today, matching this footprint is unusual. Most nearby giant spirals, grown across the universe's full lifetime with all the time in the world to spread out, still fall short of covering this much visible area. The big wheel reached a scale that plenty of modern, fully mature galaxies never quite manage, and it did so while the universe itself was still working through its earliest chapters. Every measurement so far points in the same uncomfortable direction: big, heavy, early, organized. The next detail pushes this discovery from strange into something closer to formally impossible, because size and mass alone do not prove a disk is truly settled. For that, astronomers needed to measure something far more delicate: exactly how this entire structure moves. A galaxy can look like a spiral in a picture and still turn out to be a fake, so astronomers needed proof that went deeper than shape alone. To get that proof, researchers measured motion directly, using the same basic method that revealed the big wheel's distance in the first place. Light from the side of the disk, spinning toward us, gets compressed slightly, shifting toward bluer wavelengths. Light from the side spinning away gets stretched, shifting toward redder wavelengths. By comparing those tiny shifts across the entire disk, astronomers can map out exactly how fast material orbits at every distance from the center, almost like tracing the path of every rider on a giant spinning wheel one by one. Ordinary intuition suggests a simple pattern here. Material sitting closer to the center should move fastest, since gravity from all that concentrated matter pulls hardest there, similar to how a planet closer to a star races around faster than a planet sitting much farther out. Material near the outer edge, with weaker gravity pulling on it, should slow down noticeably compared to the core. Mature, nearby spiral galaxies almost never behave that way, and this is one of the strangest, best confirmed facts in modern astronomy. Instead of slowing down toward the edges, their rotation speed stays remarkably steady across most of the disk. Astronomers call this a flat rotation curve, and it has been measured over and over in nearby galaxies for decades. The leading explanation involves an invisible, unmeasured form of matter called dark matter, spread through a much larger halo surrounding the visible disk, adding extra gravity exactly where it is needed to keep those outer speeds up. That explanation is well supported, though the true nature of dark matter itself remains one of the biggest open questions in all of physics. When astronomers measured the big wheel's rotation the same way, they found precisely that same flat, steady pattern extending across its enormous disk, exactly like the pattern seen in fully mature galaxies today. This is confirmed observation, not a rough guess based on appearance. It is one thing to see a shape that looks like a spiral in an image. It is an entirely different, far stronger kind of proof to measure motion and find the exact dynamical fingerprint that mature, settled disks carry. This distinction matters because pictures alone can be deceiving. A tangled, disorganized clump of gas can sometimes catch light in a way that vaguely resembles curling arms, especially in a blurry or low-resolution image. A measured rotation curve does not leave that kind of room for doubt. Motion either lines up into a coherent, shared pattern, or it does not, and there is very little middle ground between those two outcomes. That fingerprint changes everything about how seriously this discovery has to be taken. A flat rotation curve this early does not just suggest order. It confirms it, measured directly rather than assumed from a picture, and it sets up an even bigger question about what that kind of steady, coordinated motion actually proves about the calm this galaxy must have needed to build it. Motion tells a story that shape alone cannot, and the story hidden in the big wheel's spin is almost unsettling in how orderly it sounds. A rotation curve does more than describe speed. It describes coordination. When astronomers say a disk's rotation is smooth and steady, they mean nearly every star and cloud of gas inside it is moving in the same direction, along roughly the same flat plane, following a shared, predictable path around the center. Scientists sometimes describe this kind of disk as dynamically cold, a technical way of saying the random, scattered motion you would expect from a recently disturbed system is almost entirely absent. Contrast that with a freshly disturbed galaxy, one still reeling from a recent violent merger. Stars inside a system like that move on tilted, crossing, unpredictable paths, more like a swarm scattering after being startled than a formation moving in step. A rotation curve measured across a disturbed galaxy comes back noisy and inconsistent, nothing like the clean, steady curve found in the big wheel. The big wheel's measured rotation speed adds another layer to this picture. Material inside its disk moves at several hundred miles every second, fast enough to cross the entire real-world gap between Earth and its moon in well under half an hour. That is not a leisurely drift. It is a tremendous amount of raw motion, and yet it stays perfectly organized rather than scattering into chaos. Every part of the disk cooperating with every other part instead of working against it. Coordination on this scale does not happen by accident, and it does not happen quickly under normal conditions. It requires an environment stable enough, over a long enough stretch of time, for gravity and motion to settle into balance, rather than getting constantly reshuffled by outside disturbances. This is exactly the kind of stability the standard growth chart said should still be rare or entirely absent this early in cosmic history. There is a reason astronomers treat rotation measurements as the gold standard for judging whether a distant galaxy is truly a mature disk rather than something that merely resembles one. Shape can be an illusion of angle, distance, or image quality. Motion cannot. Once researchers had this measurement in hand, doubting the big wheel's maturity stopped being a reasonable option. This same standard gets applied to every serious claim of an early, settled disk, not just this one galaxy. Whenever a new candidate shows up in the data, rotation is the test it has to pass before anyone takes the claim seriously. Plenty of early candidates have failed that test over the years, turning out to be disturbed, noisy, or simply too faint to measure reliably. The big wheel passed cleanly, which is exactly why it earned this much attention in the first place. So, the big wheel is not simply an old-looking galaxy wearing the right shape by coincidence. It is a system proven, through direct measurement of its motion, to behave like a fully settled, mature disk. That distinction matters enormously for what comes next, because proving this level of order exists is only half the puzzle. The far harder question is explaining exactly why spiral arms require that order in the first place, and why nature normally refuses to hand it out this early. A spiral arm is not a wall or a rope stretched across a galaxy, and once you understand what it actually is, the whole mystery gets sharper. The arms curling through a disk are not fixed groups of stars traveling together forever, locked in place like beads on a string. They are patterns, moving waves of slightly higher density drifting through the disk over time. Picture the way traffic sometimes bunches up on a highway for no obvious reason. Cars slowing down, clustering tightly for a stretch, then speeding up and spreading out again once they pass the crowded patch. The jam itself moves down the highway even though individual cars are constantly entering and leaving it. A spiral arm behaves the same way, a wave of compression that gas and stars pass through, rather than a fixed structure carrying the same material forever. This matters because compression only creates a visible arm under the right conditions. Gas needs to be cold and dense enough to respond strongly when that wave passes through it, getting squeezed together enough to trigger a fresh burst of star formation. That burst of newborn, bright stars is what actually lights up a spiral arm and makes it visible from enormous distances. Hot, turbulent, chaotic gas cannot respond the same way. It resists compression, refuses to cooperate with the wave, and simply cannot organize into anything resembling a clean, glowing arm. That single requirement, cold and settled gas arranged into a thin, calm disk, is the whole reason spiral arms are considered a late-stage feature of galaxy development rather than an early one. Newly forming galaxies are full of hot, turbulent gas, stirred up by newborn stars exploding, by inflowing material crashing in, and by the general disorder of early assembly. Cooling that gas down and settling it into a flat, quiet layer capable of supporting a traveling density wave takes real time under the standard picture of galaxy growth. There is a second requirement hiding underneath the first one, and it is just as important. Even after gas cools, the disk as a whole needs rotation to dominate over random, scattered motion. Astronomers describe this balance using the idea of rotational support, essentially asking whether the organized spin of a disk outweighs the leftover jitter and scatter left behind by its formation. A disk, still shaking off recent disturbances, stays dominated by that random motion. Only once rotation clearly wins out can a stable wave, and therefore a visible spiral arm, travel cleanly through the disk without getting disrupted. This is where the big wheel becomes especially hard to explain. Building spiral arms requires calm, settled, cooled gas arranged into a stable disk with rotation firmly in control of how everything moves. The standard timeline says that kind of calm should still be scarce this early, yet here sits a galaxy with unmistakable spiral arms, fully lit, fully organized, sitting at almost exactly the age when this specific ingredient was supposed to be missing. Understanding what spiral arms need makes the puzzle sharper, not softer. It is no longer enough to ask how a galaxy grew this massive this fast. Now the question becomes how it grew calm enough, this early, to support one of the most delicate structures a galaxy can build. And calm, according to nearly everything astronomers thought they knew about the young universe, was supposed to be the rarest ingredient of all. If calm is the ingredient spiral arms need most, then collisions are the exact opposite, and the young universe was supposed to be full of them. When two galaxies collide and merge, the damage runs deeper than simply mixing two collections of stars together. Gravity from the incoming galaxy tugs unevenly on stars throughout the target disk, speeding some up, slowing others down, bending orbits that were once flat and circular into tilted, stretched, unpredictable paths. Astronomers call this general process violent relaxation, and it is remarkably effective at scrambling order that took a long time to build. The visible result is dramatic. A thin, flat, calmly spinning disk can puff up into a thicker, rounder shape after a serious merger, its stars scattered onto crossing orbits instead of neatly aligned ones. Gas inside the colliding galaxies gets shocked and heated by the encounter, driven far from the cold, settled state spiral arms require. In the most extreme mergers, a once orderly spiral can end up looking almost entirely reshaped, closer to a jumbled blob than a wheel. This is exactly why frequent mergers were considered such a serious obstacle to early spiral formation. It is not simply that young galaxies had not yet had enough time to build a disk. It is that any disk attempting to form kept getting knocked back down before it had a real chance to finish, over and over, in an environment where a major collision might strike again within a few 100 million years. Not every merger causes equal damage. A small galaxy merging into a much larger one tends to leave a lighter mark, sometimes barely disturbing the larger disk at all. A merger between two galaxies of roughly similar size does far more damage, often scrambling both systems beyond easy recognition. Distinguishing between these outcomes matters, because it means calm was never a single switch flipped on or off, but a balance that depended heavily on exactly which kind of encounter a young galaxy happened to experience. Even a single, well-timed merger can undo an enormous amount of careful settling. A disk that spent hundreds of millions of years gradually cooling and organizing itself can lose most of that progress in a single violent pass, lasting only a relatively short stretch of time by cosmic standards. Under those conditions, sustaining calm long enough to grow real spiral arms starts to look less like a difficult task and more like an outright unlikely one. Astronomers can usually spot the aftermath of a recent violent merger without much trouble. Stars scattered onto disturbed orbits, faint streams of stripped stars trailing away from a galaxy's main body, or a thickened, puffed-up disk rather than a thin, flat one, all leave a lasting signature that lingers for a long time after the collision itself has finished. None of those warning signs show up in the big wheel's measurements. Every indicator instead points toward a disk that settled cleanly and stayed that way. That is precisely the environment the young universe was expected to provide almost everywhere astronomers looked. Frequent mergers, constant disruption, a wrecking ball swinging through nearly every young galaxy's early life, again and again, resetting the clock on calm before it had time to matter. Against that backdrop, the sheer existence of the big wheel starts to look less like an unusual detail and more like a direct contradiction sitting right at the center of the story. Every thread of this story now pulls tight around a single, uncomfortable contradiction. On one side sits the standard growth chart, built from decades of careful observation and enormous computer simulations. That chart says the early universe should have been dense, crowded, and violent, packed with frequent mergers capable of scrambling any disk attempting to settle. It says calm, cold, organized gas, the exact ingredient spiral arms require, should have remained rare or entirely absent for a long stretch of cosmic time. This picture is not a fringe guess. It explained the broader universe reasonably well for years. On the other side sits the big wheel itself, measured directly rather than merely photographed. A disk stretching over 100,000 light-years across, a mass roughly 5 times that of our own galaxy. A flat, steady rotation curve identical to the fingerprint carried by fully mature, nearby spirals. Spiral arms bright enough and coherent enough to be identified with confidence from billions of light-years away. All of it sitting at an age representing only a small fraction of the universe's entire life so far. Both of these things are confirmed. The theory is well supported by extensive prior evidence. The observation is well supported by careful, cross-checked measurement. Yet they cannot both be completely accurate in their current form, because one predicts chaos at this exact age, and the other delivers, in direct contradiction, calm. Scientific tension like this does not get resolved by simply picking the side that feels more comfortable. It gets resolved by more data, more careful checking, and more candidate explanations tested against reality until one of them survives every attempt to break it. That process is already underway, and it is far from finished, which is exactly why this particular contradiction has drawn so much attention from researchers well outside the original team that found it. This is the exact shape a genuine scientific mystery takes. It rarely arrives as a single wrong fact sitting isolated somewhere. It arrives as two well-supported things refusing to fit together cleanly, forcing researchers to figure out which piece needs to bend, or whether an entirely new piece is missing from the picture altogether. Perhaps mergers were less frequent in some regions than the models assumed. Perhaps gas can cool and settle far faster than anyone previously calculated. Perhaps something about this particular environment allowed it to skip stages other galaxies could not skip. Every one of those explanations remains a candidate. None of them has been confirmed yet. What is confirmed, beyond reasonable doubt, is that the paradox itself is real, sitting inside data too solid to dismiss and too strange to fully explain. It is worth pausing on how rare this situation actually is. astronomy produces plenty of strange, one-off objects that quietly get explained within a year or two once a bit more data comes in. A contradiction, this direct, sitting between two well-tested pillars of the field, does not come along nearly as often. The people closest to this discovery, the researchers who found it and checked it and rechecked it, have their own blunt way of describing exactly where that leaves them. Scientists rarely admit defeat in public, so when they do, it is worth paying close attention. The astronomer who helped confirm the big wheel's true nature described it in stark terms once the numbers were locked in. He called it a true outlier, a galaxy that stands apart from essentially everything else found at a similar age. That phrase alone signals something significant. Outliers in science are not simply unusual. They are data points that refuse to fit inside the boundaries every existing model drew around what should be possible. Pushed further on how something this organized could have formed this early, the same researcher offered an answer far more honest than reassuring. He called it, in his own words, a complete mystery, a genuine, open, unresolved question, sitting at the center of an otherwise well-confirmed discovery, the kind of gap that no minor calculation or small correction is likely to close on its own. Statements like that carry weight precisely because scientists are trained to avoid them. Careers get built on careful, cautious language, on hedging claims until the evidence is overwhelming. When a researcher drops that caution and simply admits the honest limit of current understanding, it usually means the puzzle in front of them is real, significant, and nowhere close to solved. This kind of honesty matters, and it deserves to be marked clearly rather than glossed over. Confirmed observation. The galaxy exists, its distance is measured, its mass, size, and rotation have all been checked. Leading theory. Standard models of galaxy growth, tested successfully across countless other systems. Genuine open mystery. Exactly how a galaxy this settled managed to assemble itself this early, when the surrounding universe should have made that kind of calm nearly impossible to reach. Admitting a mystery is not the same as admitting failure. It is, in many ways, the most productive moment in any scientific investigation, the exact point where a field stops repeating comfortable assumptions and starts hunting for a genuinely new explanation. Every major shift in how scientists understand the universe has started from exactly this kind of admission. A respected researcher looking at solid data and simply saying, honestly, that the current picture does not add up. Researchers have floated early, tentative ideas. An unusually dense, gas-rich neighborhood might have fed this galaxy material faster than typical regions could manage. A quieter than average merger history might have given it more uninterrupted time to settle than most of its neighbors received. Both remain candidate explanations rather than settled answers, openly labeled as such by the very people proposing them. None of this is speculation dressed up to sound dramatic for an audience. It is the ordinary language of working scientists describing a result they genuinely cannot yet explain, printed in the same careful, peer-reviewed papers that reported the big wheel's distance, mass, and rotation in the first place. Confirmed measurement and open mystery are sitting side by side in the exact same publication, and both deserve to be taken exactly as seriously as the other. One galaxy, on its own, could always be dismissed as a rare fluke, an unlikely outlier that slipped through the cracks of an otherwise solid model. That comfortable dismissal became a lot harder to make once astronomers stopped looking at just one galaxy and started counting hundreds of them instead. A single strange result can always be an accident. A pattern repeated hundreds of times cannot. After the big wheel drew attention across the field, a separate team of researchers set out to answer a bigger, more systematic question. Instead of studying one unusual galaxy in detail, they aimed this same telescope at a wide stretch of sky and gathered a large, careful sample of ancient galaxies, all sitting within the same general era as the big wheel and even earlier. Their goal was simple to state and enormous to actually carry out. sort every one of these ancient systems by shape and see what pattern, if any, emerged across the group as a whole. The scale of the project was significant. Researchers examined roughly 850 separate galaxies, all dating back to somewhere between about 500 million and 2 billion years after the beginning of the universe. That range covers exactly the stretch of time the standard growth chart identified as the roughest, most chaotic chapter in a young galaxy's life. If the demolition derby model held up, this sample should have been overwhelmingly clumpy, patchy, and irregular, with organized disks showing up only rarely, if at all. Earlier attempts at this exact kind of survey existed too, carried out using an older space telescope working mainly in visible light rather than infrared. Those earlier surveys generally supported the standard picture, showing an early universe that looked appropriately rough and unfinished the further back astronomers looked. That older evidence was not sloppy or careless. It simply could not resolve the same fine detail this newer, more sensitive telescope was built to capture, which meant it may have been missing structure hiding just below its resolution limit the entire time. Classifying galaxy shape at this distance is a careful, painstaking process, not a quick glance. Researchers examined detailed structure in each galaxy's light, checking for the smooth, symmetrical profile of a disk against the patchy, uneven profile of an irregular system, while also watching for the dense central bulge that some more evolved galaxies carry. This kind of careful sorting, done consistently across hundreds of separate targets, is exactly what turns one interesting anecdote into a real statistical result, capable of actually testing a scientific model rather than just poking at it. Researchers also cross-checked their visual classifications, using automated measurements of each galaxy's structure, comparing brightness patterns mathematically rather than relying purely on human judgment, which helped guard against the natural bias that can creep in when scientists already suspect what pattern they are hoping to find. Running a study at this scale takes enormous effort, and it only makes sense to attempt it once a single result has already raised a serious enough question. The big wheel did exactly that. It forced a choice between treating an extraordinary object as a meaningless fluke or taking it seriously enough to check whether it had company. The answer that came back from this wider search landed harder than almost anyone on the research team expected going in. A survey of this size also does something a single striking discovery never can. It lets scientists ask how common a phenomenon actually is, rather than just confirming that it can happen at all. Rare exceptions can slip past even careful models without breaking them. Widespread, repeated patterns cannot slip past unnoticed, and that is precisely the category this result was about to fall into. Numbers do not care about expectations, and the numbers from this survey refuse to cooperate with the standard chart. According to the demolition derby model, the fraction of orderly disk galaxies should drop sharply the further back in time researchers look, while the fraction of clumpy, irregular systems should climb just as sharply, eventually dominating the sample almost entirely near the earliest end of the range. That was the expected trend line, a steep, obvious slope moving from mostly organized in the recent universe to mostly chaotic in the ancient one. The actual results, confirmed through careful, peer-reviewed analysis, showed something far flatter. The fraction of galaxies with a clear disk shape declined only slightly, moving back through this entire 2 billion year window. Meanwhile, the fraction of galaxies with an irregular, clumpy shape stayed roughly constant across that same stretch of time, never climbing the way the standard model predicted it should. Disks were not rare, exceptions scattered through a chaotic crowd. They showed up again and again, consistently, across the full range this survey covered. Picture the expected trend line as a steep hill, chaos climbing sharply the further back you travel. The actual data traced something closer to a gentle, nearly flat slope instead, barely dipping even at the very edge of what this survey could reach. A model predicting a steep hill and receiving a flat line back is not a small miss. It is the kind of gap that forces a serious rethink rather than a minor patch. The researchers leading this work were careful and precise about what actually surprised them, and their framing matters. The surprise was not that organized disk galaxies existed this early. A handful of individual examples like the Big Wheel had already hinted at that possibility. The real surprise was seeing so many of them spread consistently across hundreds of separate systems rather than showing up as a rare, isolated exception. That distinction, one strange object versus a genuine widespread pattern, is exactly what turns an anecdote into a real crack in a scientific model. This result deserves to be marked clearly. It is confirmed observation, drawn from a large, carefully classified sample rather than a single striking image. It directly contradicts a specific, testable prediction made by the standard growth chart, a prediction built on real physics that had performed well in other contexts. Contradicting a well-supported prediction this cleanly, with this much data behind it, is not something the field of astronomy takes lightly. Other research teams, working with overlapping but separate samples of ancient galaxies, have reported broadly similar patterns since this first large census was published. That kind of repeated, independent agreement across different teams is exactly what separates a fluke statistical wobble from a genuine feature of how the early universe actually behaved. The disks were not a mirage produced by one particular team's methods. They kept showing up no matter who went looking. Once that pattern became clear, an unavoidable and slightly unsettling question followed close behind. If organized disks were already this common, even in the very earliest galaxies these surveys could reach, had astronomers actually managed to observe true galactic infancy at all? Or had they simply run out of telescope before catching the universe still in its roughest, messiest, truly newborn state? Here is an idea worth sitting with carefully, because it reframes everything covered so far, and it remains a genuine open question rather than a settled conclusion. If disks are already common by the time galaxies reach roughly 500 million years old and stay common all the way through 2 billion years, then the earliest galaxies these surveys managed to capture may not represent the true starting point of galaxy formation at all. They may already be somewhat advanced, somewhat settled, sitting past the roughest opening stage rather than inside it. Researchers involved in this work have said plainly that they suspect they are not yet seeing the earliest stages of galaxy formation, an honest admission that the current view, however impressive, still has a real ceiling. This possibility matters because it changes what kind of mystery this actually is. It is one thing to imagine a handful of unusually lucky galaxies skipping ahead of schedule under rare, special conditions. It is a much bigger claim to suggest that organizing into a disk might simply be a faster, more ordinary process than anyone previously assumed, something most young galaxies manage relatively quickly rather than something only a lucky few pull off. Think about how strange that would make our own cosmic backstory. If settling into a spinning disk really is closer to the default outcome for a young galaxy than the rare exception, then countless ordinary systems scattered across the sky, not just the handful astronomers have singled out for special attention, might share this same accelerated history. That would turn a striking anomaly into something closer to a hidden rule. Nobody currently knows for certain which of those two pictures is closer to correct, and that uncertainty deserves to be stated honestly rather than smoothed over. It remains an open theoretical question, actively debated within the field, whether the young universe was calmer overall than older models assumed, or whether galaxies simply have tools for settling quickly that current simulations have not yet fully captured. Resolving that question will likely require reaching even further back than current instruments allow, catching galaxies at ages so young that if disks still turn out to be common there too, the standard growth chart would need far more than a minor adjustment. It would need a genuinely new chapter, describing a young universe that organizes itself on a timescale nobody had seriously entertained before this evidence started arriving. What is confirmed is narrower, but still striking on its own. Every galaxy examined so far, across the entire window these surveys could reach, sits closer to the organized end of the spectrum than the standard growth chart predicted for its age. Even the very earliest, most distant galaxies in these samples already show meaningfully more structure than expected. That leaves an uncomfortable gap sitting right at the edge of what current telescopes can reach. Somewhere further back, closer to the true beginning, either galaxies eventually do look as rough and chaotic as originally predicted, or they simply do not. And the entire model of how quickly structure builds itself after the beginning of everything needs a far more serious rewrite than most scientists expected to be writing this soon. Spiral shape turned out to be only one half of a much larger problem, quietly building inside the same data. Alongside the disk question, a separate but closely related puzzle has been growing across the wider field of early universe astronomy. Surveys using this same telescope have been turning up galaxies that are organized ahead of schedule, more numerous than expected, and considerably brighter than the standard growth chart predicted for such an early era. Both problems point toward the same underlying suspicion. Something about how fast galaxies assemble and light up in the young universe is not quite matching the model. A researcher at a major national research laboratory summed up the core dilemma in especially blunt terms. Either there is a genuine overabundance of galaxies sitting in the early universe, more of them than the standard model expects to find, or the galaxies that do exist are considerably brighter, and therefore more massive or more actively forming stars than current models account for. Both possibilities carry serious consequences, and neither one is a comfortable fix. This broader puzzle is separate from the spiral shape question covered earlier in this story, but the two clearly rhyme with each other. Both point toward early galaxies doing more, faster, than anyone expected them to be capable of doing. Whether that means gathering more mass more quickly, organizing into calmer structures more quickly, or lighting up with more stars more quickly, the common thread running through all of it is speed. Something about the young universe seems to let galaxies grow up faster than the standard timeline allows. It helps to keep these two puzzles distinct even while noticing how closely they overlap. The spiral shape problem concerns order, meaning how galaxies arrange their motion and structure. The brightness and abundance problem concerns quantity, meaning how much mass and light young galaxies manage to produce in a limited stretch of time. A full explanation for the young universe may eventually need to solve both at once, rather than treating them as two unrelated coincidences happening to show up during the same era. Researchers investigating this broader brightness and abundance problem have proposed several possible explanations, and it is worth naming them honestly as candidates rather than settled fixes. Perhaps gas flows into forming galaxies more efficiently than current models assume. Perhaps the physical processes that normally slow down star formation, collectively called feedback, are weaker in the early universe than expected, letting stars form faster and brighter than predicted. Perhaps early galaxies contain less dust than assumed, letting more of their light escape and reach our telescopes without getting absorbed along the way. None of these explanations has been confirmed as the answer, and it is entirely possible more than one of them is contributing at once. What is confirmed is the pattern itself, repeated across multiple independent surveys studying different aspects of the same early era. Somewhere in the recipe for building a young galaxy, an ingredient is working faster, or in larger quantity, than the standard chart accounted for, and untangling exactly which ingredient is responsible has become one of the most active investigations in the entire field. Real scientific results get stronger, not weaker, when a completely different tool finds the same answer. Everything covered so far relied on this one telescope, using infrared light and its infrared instruments to study distant galaxies. Independent confirmation matters enormously in science, and it arrived from an entirely different kind of observatory, a vast array of radio dishes spread across a high desert plateau in Chile, built to detect a completely different type of light than the one this story has focused on until now. That facility, the Atacama Large Millimeter Array, detects radio and millimeter wavelength light emitted by cold gas and dust. Rather than the infrared starlight, this telescope specializes in catching. Using a completely different physical process to measure motion, researchers pointed this array at a distant galaxy and tracked the glow of cold gas across its structure, watching for the same kind of blue shift and red shift signature used earlier in this story to measure rotation. This facility sits at extremely high altitude on a plateau chosen specifically for its thin, dry air, conditions that keep water vapor from blocking the faint millimeter wavelength signals researchers rely on. Dozens of separate dish antennas work together there, effectively acting as a single, enormous telescope capable of picking out extremely faint, extremely precise detail from targets scattered across the observable universe. The result matched the broader pattern already building across this entire investigation. The gas showed clear, coherent motion, moving toward observers on one side of the galaxy and away on the other. Exactly the signature expected from an organized, rotating disk rather than a chaotic, disorganized cloud. Researchers involved in the discovery described it as the most distant rotating disk galaxy confirmed at the time, a genuinely independent data point supporting the same conclusion the Big Wheel and the wider disk survey had already been pointing toward. What makes this cross-confirmation especially convincing is how different the two detection methods really are. One relies on measuring starlight stretched into infrared wavelengths. The other relies on measuring the faint glow of cold gas at wavelengths far longer than infrared, gathered by antennas rather than mirrors. Two teams, working with different equipment, different wavelengths, and different raw data, still walked away with the same basic verdict about how this galaxy moves. Independent confirmation, using an entirely separate instrument built around entirely different physics, carries serious weight in science. It rules out the possibility that this whole pattern is somehow an artifact specific to one telescope, one detector, or one particular way of processing infrared light. Two very different tools, studying two very different types of light, arrived at the same conclusion: organized, rotating disks were forming earlier in cosmic history than the standard model expected. This cross-confirmation did more than simply back up what had already been found. It pushed the boundary of the entire investigation even further back in time, toward a version of the young universe so early that almost nobody expected to find anything this organized surviving there at all. Every chapter of this story has been sliding the timeline earlier, and this one slides it further than any before it. The rotating disk, detected by that array of radio dishes, sits at an age that makes the Big Wheel look almost comfortably late by comparison. Its light left the galaxy roughly 700 million years after the beginning of the universe, a moment when the universe had lived through only about 5% of its current age. 5%. If the Big Wheel already felt impossibly early at around 15%, this galaxy sits at barely a third of that fraction, deep inside a stretch of cosmic history astronomers usually describe as still forming its very first generations of galaxies. This is confirmed observation, cross-checked using the gas motion measurements described in the previous chapter, not an estimate built on shape or appearance alone. A galaxy this early, showing rotation this coherent, pushes directly against the earliest edge of when astronomers expected any organized structure to exist whatsoever. The standard model does allow for small, early galaxies to begin forming around this general era. It does not comfortably allow for one of them to already behave like a calm, rotation-dominated disk. At 5% of the universe's current age, the very first stars in the universe had only just begun forming in large numbers, lighting up a cosmos that had spent its earliest stretch sitting mostly dark. Finding an organized, spinning system already assembled, this early places it uncomfortably close to that opening chapter, a period astronomers still consider one of the least understood stretches of the entire cosmic story. Researchers studying this system described it as strongly rotation-dominated, a technical way of saying its motion overwhelmingly favors organized spin over scattered, random movement, the same defining trait that made the big wheel's rotation curve so significant several chapters ago. Finding that same defining trait this much earlier suggests the ability to organize into a coherent disk may not require nearly as much accumulated cosmic time as the standard growth chart assumed. Astronomers were careful to note that this system is smaller and less massive overall than the big wheel, closer in scale to a young, still developing galaxy than a fully grown giant. That distinction matters. It shows organized rotation is not limited to rare, unusually massive systems that somehow found a shortcut. It can apparently take hold in smaller, more ordinary early galaxies as well, which makes the underlying explanation feel even more fundamental rather than more like a fluke. Consider what 5% of the universe's current age actually represents. Using the same imagined 100-year human lifetime from earlier in this story, this galaxy had already achieved coordinated, disk-like rotation before that lifetime reached its 5th birthday. Under the standard timeline, a structure like this was expected to still be a scattered handful of newborn stars, not a working, spinning system with measurable, organized motion. 2 separate discoveries, using 2 separate telescopes and 2 separate physical methods, now agree on the same unsettling point. Organized rotation can apparently exist far earlier than anyone confidently predicted before this evidence arrived, and this particular ancient system was not finished revealing what it had to offer. Buried within its structure, researchers began noticing hints of something even more specific and even harder to explain than rotation alone. Rotation alone would already have been a major discovery. What researchers noticed layered on top of that rotation pushed the story even further. Looking closer at the detailed structure of this extremely early rotating disk, researchers spotted faint hints of 2 additional features, both instantly familiar to anyone who studies nearby spiral galaxies. The first was a suggestion of spiral arms, curling patterns of gas woven through the disk, echoing the exact kind of structure covered earlier in this story. The second, arguably even stranger, was a hint of a central bar, an elongated, straight feature of stars and gas, stretching directly across the galaxy's middle rather than curving around it. A central bar is not a simple decoration either. It forms only within a disk, stable enough for gravity to organize stars into this specific elongated pattern, and it plays an active role once it exists, funneling gas from the outer disk down toward the galactic center and helping to feed whatever sits there, often a massive black hole. Many mature spiral galaxies nearby carry a bar just like this one, our own galaxy included, its own central bar mapped in detail by astronomers studying our home skies. Finding hints of a bar this early carries real weight, though it deserves an honest, careful label. These particular features are described by researchers as tentative, a genuine early indication rather than a fully confirmed, locked-in structure. Confirming details this fine at this staggering distance pushes current instruments close to their absolute limit, and follow-up observations will be needed before anyone treats a bar at this age as settled fact rather than a strong early hint. A bar takes even more coordinated behavior to build than an ordinary spiral arm does. Where a spiral arm is essentially a traveling wave of compression, a bar requires a large fraction of a disk's stars to settle into stretched, elongated orbits that stay locked together, reinforcing each other over time rather than drifting apart. Nearby galaxies that carry bars are almost always older, thoroughly settled systems, which makes even a tentative hint of one this early feel especially significant. Even held to that cautious standard, the implication is hard to ignore. A bar requires a disk stable enough and settled enough to organize an entirely separate structural feature layered on top of ordinary rotation. If confirmed, it would mean this galaxy, sitting at roughly 5% of the universe's current age, had already developed structural sophistication that mature. Nearby galaxies took much longer to build, doubling down on exactly the same paradox introduced by the Big Wheel several chapters earlier. Future observations, using longer exposure times and sharper imaging, should eventually settle whether this particular hint holds up. Astronomers are already planning follow-up studies aimed directly at this question, treating it as one of the higher priority targets worth revisiting with fresh data. Until then, it stands as a promising early clue rather than a locked conclusion, exactly the kind of loose thread that keeps an entire field of research pushing forward. Two separate ancient systems, discovered years apart using different telescopes, both hint at internal structure that should have needed vastly more time to develop. That repetition is not a coincidence anyone in this field is comfortable dismissing anymore. It points toward a bigger, more sweeping question about just how much cosmic time galaxies actually require to organize themselves, one that reaches far beyond any single galaxy this story has covered so far. Every discovery in this story so far has been chipping away at the same number, and it is worth stepping back to see exactly how far that number has moved. The standard growth chart, built and tested over decades, once suggested that building a fully organized spiral disk, complete with a flat rotation curve and visible arms, generally required something close to half the universe's entire lifespan, sometimes more. That estimate was not pulled from thin air. It came from real physics, describing how long gas takes to cool, how often galaxies were expected to collide, and how much calm time a disk needs to settle after a disruption. Real observations have now chipped huge pieces off that estimate, one confirmed discovery at a time. The Big Wheel showed a fully organized, massive spiral disk existing at roughly 15% of the universe's current age. The wider census of hundreds of ancient galaxies showed organized disks were common, not rare, across that same broad era. The rotating system detected using cold gas pushed organized rotation back even further to roughly 5% of the universe's current age, with hints of even finer structure layered on top. Line those results up together, and the picture shifts dramatically. Instead of needing something close to half the universe's lifespan, meaningful galactic organization now appears to be achievable within a small fraction of that time, potentially within the first billion years, or even less for at least some systems. That is not a minor correction to an existing model. That is a compression of the expected timeline by a wide enough margin to force real structural changes to the underlying theory itself. Put another way, an estimate that once measured this process in terms of several billion years is now being challenged by evidence measured in a fraction of a single billion years. That is not a small revision sitting comfortably within the model's existing margin of error. It is a difference large enough that the old chart and the new evidence genuinely cannot both be describing the same, simple, gradual process. It is important to be precise about what this compression does and does not prove. It does not mean every galaxy in the early universe organizes itself this quickly. Plenty of confirmed, genuinely clumpy, chaotic galaxies still show up throughout this same era, exactly as the standard model expected. What the evidence increasingly suggests is that fast, coordinated organization is possible far earlier and far more often than anyone previously believed, even if it remains just one path among several that early galaxies can follow. That leaves two very different populations sharing the same slice of cosmic history, side by side. Rough, unsettled, still-forming galaxies exist right alongside fully organized, mature-looking disks at essentially the same moment in the timeline. Explaining why some galaxies took the fast path while their neighbors stayed chaotic has become its own separate puzzle, layered directly on top of the original mystery this story set out to explain. That distinction, possible and common rather than universal, still leaves an enormous mystery standing at the center of this entire investigation. Something is allowing a meaningful fraction of early galaxies to skip past the rough, chaotic phase that theory once treated as a mandatory rite of passage. Figuring out exactly what that something is has become one of the most urgent open questions in the entire field of galaxy formation. Every mystery in science eventually needs a real explanation, and this one still does not have a confirmed answer. Several candidate explanations are actively being tested right now, and none of them has yet earned the label of settled fact. One idea suggests dark matter, the invisible material providing much of a galaxy's gravity, might clump together and settle faster in the early universe than current simulations assume, giving ordinary gas a stable gravitational framework to organize around sooner than expected. This remains a working hypothesis, tested through updated computer models rather than direct measurement, since dark matter itself has never been directly detected. A second idea focuses on gas itself, suggesting that cold streams of material may be able to flow directly into forming galaxies along narrow, efficient channels, arriving already relatively calm and organized, instead of crashing in through disruptive, chaotic mergers. If gas can reach a young galaxy this smoothly, the long, slow settling period the standard chart assumed might simply not be as necessary as once believed. Evidence for this idea exists in certain simulations, though direct observational confirmation remains limited and genuinely incomplete. A third idea points toward environment, the same explanation floated earlier for the big wheel specifically. Some patches of the early universe may have been calmer and less crowded than average, giving galaxies born there extra breathing room to settle without constant disruption from nearby mergers, even while the wider universe stayed rougher overall. This would help explain why organized disks show up often, without requiring every single early galaxy to follow the same accelerated path. None of these explanations has been ruled out, and none of them has been confirmed as the complete answer either. It is entirely possible the real explanation borrows a piece from each idea, rather than resting on any single cause alone. That kind of layered, multi-part answer is common in astrophysics, where messy, complicated real conditions rarely reduce down to one clean, single cause. Testing these ideas properly means comparing detailed predictions from updated simulations against real, measured galaxies, like the Big Wheel and the rotating disk found even earlier. Where a simulation's predicted mass, size, or rotation lines up with what telescopes actually measure, that candidate explanation gains support. Where it fails to match, researchers know exactly which assumption needs to be reworked, a slow, careful process of elimination playing out across research groups worldwide right now. Resolving this properly will likely require future instruments capable of reaching even further back in time than current telescopes can manage, combined with far larger surveys capable of testing these ideas across thousands of galaxies rather than dozens. Several ground-based and space-based projects currently in development are being designed with exactly this kind of question in mind, built to gather sharper detail from fainter, more distant targets than even this telescope can currently manage. Until that evidence arrives, this remains exactly what honest scientists have already called it, a genuine, unresolved, actively investigated mystery, sitting at the center of one of the biggest open questions left in the story of how the universe built itself. Step back from every individual measurement in this story, and one enormous idea remains standing in the middle of all of it. Our own galaxy carries the exact same basic shape as the Big Wheel, a flat, spinning disk, curling arms, a steady, coordinated rotation carrying our star, our planet, and everything on it around a shared galactic center. For a long time, the standard story assumed our galaxy needed most of the universe's entire history to become this organized, patiently assembling itself across billions of years of gradual settling. Everything uncovered in this investigation suggests that assumption may need serious revision. If galaxies really can organize themselves within a small fraction of the universe's total age, then the deep, patient, billions of years version of our own galaxy's origin story might be only part of the picture. Some of the calm, coordinated structure we depend on, the very structure that eventually allowed a stable, quiet corner of space for a planet like ours to form and hold steady for billions of years, may have snapped into place far faster than anyone assumed, earlier in cosmic history than most models ever considered possible. None of this means our galaxy's full story is settled or fully understood. It means the opening chapters may have unfolded on a very different clock than the one most people, including most working astronomers, assumed just a few years ago. That kind of shift rarely stays contained inside one narrow corner of a field. It tends to ripple outward, forcing scientists to revisit conclusions in nearby areas that once seemed completely unrelated. That idea reaches further than astronomy alone. Everything about how we picture the universe rests on a certain expected pace, order building slowly, generation after generation, chaos gradually giving way to structure over enormous stretches of time. The big wheel, the wider census of hundreds of ancient disks, and the rotating, possibly barred system found even earlier, all point toward a universe capable of organizing itself far faster than that expected pace allows. If the timeline for something as complex as a galaxy can compress this dramatically, every assumption about how quickly complexity can emerge from raw chaos deserves a second, harder look. Nobody currently has a complete answer for how nature pulls this off, and that gap is not a weakness in this story. It is the most exciting part of it. Genuine mysteries are rare in a field as mature as astronomy, and this one sits wide open, waiting on the next observation, the next survey, the next impossible galaxy hiding quietly in existing data, waiting for someone to notice it. Think back to where this story started, a single strange image that should not have been possible. It grew into a galaxy with a name, then a distance, a mass, a size, and a rotation that proved its order beyond doubt. It grew again into hundreds of similar systems, then into a second galaxy, pushing the timeline back even further, carrying hints of a bar and arms of its own. Every step widened the same simple, staggering idea. The universe may build real, lasting order far faster than we ever gave it credit for. Somewhere out past the edge of what any telescope has confirmed so far, more of these impossible, perfectly organized ancient wheels are almost certainly still spinning, patient and silent, waiting their turn to rewrite the timeline all over again. One of those quiet, impossible wheels has already been found, and it sits a full billion years earlier than the big wheel. While one team was studying the big wheel in detail, another group was running a survey with a very different strategy. Instead of pointing this telescope at a chosen target, they let it collect images of whatever happened to sit near its main observations, a kind of skywatching in the margins. Thousands of galaxies drifted through those margins. Most of them looked exactly as expected for their age, small and rough and unfinished. One of them did not. Researchers named it Zhulong, after a torch dragon from ancient Chinese mythology, a creature whose open eyes were said to bring daylight to the world. The name fits an object whose light has been traveling toward us for close to 12.5 billion years. Its light left when the universe was roughly 1 billion years old, about 7% of its present age. What makes Zhulong remarkable is how familiar it looks. It has a bright central region packed with older stars, surrounded by a broad, flat disk where new stars are still forming, with clear spiral arms sweeping outward through that disk. Astronomers call this a grand design spiral, the same category our own galaxy belongs to. Its disk stretches more than 60,000 light years from edge to edge, and its total mass in stars is close to what our own galaxy holds today. Take a moment with that comparison. A galaxy carrying roughly the same mass as ours, with the same layered structure of old center and young disk, already assembled before the universe had finished its first billion years. Under the standard growth chart, our own galaxy needed the better part of 10 billion years to reach this state. Zhulong appears to have managed it in a fraction of that time. There is a careful label to attach here. Zhulong's age comes from the colors of its light, measured across many filters, a method astronomers trust but one that carries more uncertainty than the direct spectral measurement used for the big wheel. Follow-up observations designed to lock its distance in place are planned, and until they arrive, its exact age remains an excellent estimate rather than a confirmed fact. The shape, the arms, and the layered structure, however, are plainly visible in the images themselves. Even with that caution in place, the discovery lands hard. Zhulong is not a small system that happened to spin early. It is a full-sized galaxy with the architecture of a mature spiral, sitting in an era when the standard model expected nothing more than clumps and fragments. If the age estimate holds, it becomes one of the earliest full spirals ever seen and a direct cousin of the galaxy you are lying inside tonight. The team also noticed something subtle in its center. That central region appears to have already slowed or stopped forming new stars, a sign of maturity that nearby galaxies typically reach only after billions of years of evolution. A galaxy with a quiet, finished core and a lively, star-forming disk is a galaxy that has already lived through several distinct stages of growth. So, the timeline slides earlier once again, and a new pattern begins to take shape. Organized spirals are not just showing up early, they are showing up early with all the features of galaxies that should be far older. And one of those features, a straight bar of stars cutting across a galaxy's heart, turned up next, in a place nobody expected to find it. A bar across the center of a galaxy is one of the last things a disk builds, which is exactly why finding one this early caused such a stir. Earlier in this story, researchers spotted faint hints of a bar inside an extremely early rotating disk, and that hint was rightly labeled tentative. This chapter concerns a different galaxy, one where the bar is not a hint at all. It is plainly visible, stretching straight across the center of a spiral disk in images taken by this telescope during one of its first large surveys of the early universe. Astronomers catalogued it under a survey code, so for tonight we can simply call it the early barred spiral. Its light left roughly 2 billion years after the beginning, placing it in the same broad era as the big wheel. In mass, it sits close to our own galaxy. In shape, it looks like something you might find in a modern galaxy atlas, a bright bar of stars with spiral arms curling away from each end, the same structure our own galaxy carries at its center. Why does a bar matter so much? Think of a disk of stars as a crowd of skaters circling a rink. In a young, chaotic galaxy, the skaters weave in every direction and nothing holds together. A bar forms only when a large group of skaters falls into the same stretched, elongated loop and stays there, lap after lap, reinforcing the pattern rather than breaking it. That takes a disk that is already calm, already thin, and already dominated by orderly rotation. Astronomers describe a barred disk as dynamically settled, and settling was supposed to take most of the universe's history. This is confirmed observation, published after peer review, and the researchers involved were candid about the shock. Before this telescope, the earliest clearly barred galaxies dated from roughly half the universe's current age. This one pushed that boundary back by billions of years in a single image. The team wrote that the discovery challenges current ideas about how quickly galaxy disks stabilize, which in the careful language of a research paper is a strong statement. The bar carries a second meaning too. Once a bar exists, it acts like a slow conveyor belt, dragging gas from the outer disk inward toward the center. That inflow feeds new star formation near the core and can feed a central black hole as well. A galaxy with a bar this early is not only structurally mature, it has already switched on the internal machinery that shapes how a galaxy grows for the rest of its life. Computer simulations have been run since the discovery to see whether a bar can form this fast under any reasonable conditions. Some of them can produce early bars, provided the disk becomes cold and thin very quickly and avoids major disruption. Those same conditions are precisely the ones the standard growth chart considered unlikely in the young universe. The bar, in other words, does not just sit oddly on the timeline. It tells astronomers something specific about the calm conditions that must have existed around this galaxy. Nearly every galaxy in this story so far was found by this one infrared telescope. Yet the first clear warning that early disks were possible came from a completely different instrument several years before this telescope ever left the ground, and almost nobody outside the field noticed it at the time. Sometimes the universe sends a warning early, and the field is simply not ready to hear it. Years before this infrared telescope reached space, the radio array in the Chilean desert was already studying a distant galaxy in a way that should have raised alarms. Astronomers had found this galaxy by a clever trick. They used the light of a distant quasar, much as in the Big Wheel's own discovery, and looked for the shadow of gas sitting between that quasar and us. The gas revealed a galaxy, and the array was pointed at it to see what the gas was doing. What the gas was doing was rotating smoothly and steadily in a flat disk. Researchers named it the Wolf disk, in honor of an astronomer who had spent his career arguing that such gas-rich systems deserved more attention. Its light left about 1.5 billion years after the beginning. The disk was spinning at roughly 170 miles per second, a speed comparable to the rotation of our own galaxy today. That result was confirmed observation, published in a major journal, and it did not fit the standard growth chart. A cold, orderly, fast-spinning disk was not supposed to exist at that age. Most astronomers at the time treated it the way any careful scientist treats a single strange result. They noted it, discussed it, and largely filed it as an interesting exception that would need company before anyone rewrote a model. The Wolf disk also carried a clue about how such a galaxy might form. Its gas was cold, and cold gas is the raw material of orderly disks. Hot, turbulent gas swirls in every direction and resists settling. Cold gas sinks, flattens, and rotates. Finding so much cold gas already gathered into a disk this early suggested that whatever fed this galaxy delivered its material gently, without the violent heating that mergers produce. That was the first observational hint of the smooth gas streams that later became a leading candidate explanation in this story. Consider how the timing of that discovery shaped the field. When this new telescope launched and began returning images of early disks, astronomers already had a reference point. The Big Wheel, the wider census, the early barred spiral, and the twin of our own galaxy did not arrive into a field with no warning at all. They arrived into a field that had been handed a single strange piece years earlier and had not yet known where it fit. Seen from tonight, the Wolf disk reads like the opening line of a story that took several more years to unfold. One instrument, working in cold gas, found an orderly disk far too early. A second instrument, working in infrared starlight, then found dozens more. 2 different kinds of light, 2 different physical signals, and one consistent message about how quickly the young universe could organize itself. There is a lesson tucked inside this chapter about how science actually moves. A single anomaly rarely changes anything on its own, and it should not. What changes a model is the slow accumulation of independent results that refuse to go away. The Wolf disk was the first stone. The rest of this story is the pile that grew on top of it. And the pile was about to grow in a direction nobody was watching, because the next surprise was not a galaxy still forming stars. It was a galaxy that had already stopped. There is something stranger than a galaxy growing up too fast. It is a galaxy that grew up, finished, and shut down, all before the universe reached its first birthday. Galaxies form stars out of cold gas, and as long as gas keeps arriving, the stars keep coming. Astronomers use the word quiescent for a galaxy that has stopped. Its gas supply has run out or been heated beyond use, its young blue stars have faded, and what remains is a quiet population of older, redder stars slowly aging together. Nearby, quiescence is usually a sign of great age, the galactic equivalent of retirement after a long working life. This telescope found a retired galaxy whose light left roughly 700 million years after the beginning. That places it at around 5% of the universe's current age, the same era as the rotating disk with hints of a bar covered earlier tonight. Researchers measured its light in detail with a spectrograph, an instrument that spreads light into its component colors, and the result was clear. The signatures of active star formation were missing. The galaxy had formed its stars in a short, intense burst and then gone quiet. This is confirmed observation. The team estimated that the burst of star formation lasted perhaps a few tens of millions of years and then ended abruptly, tens of millions of years before the moment the light was captured. In cosmic terms, that is a galaxy that lived an entire working life and retired within a window shorter than the time it takes our own star to complete a few orbits around the galactic center. Why would a galaxy stop so soon? Several possibilities are being tested, and none is confirmed. Perhaps the burst of star formation was so violent that the resulting stellar winds and explosions blew the remaining gas out of the galaxy entirely. Perhaps a young black hole at its center heated the surrounding gas until it could no longer cool and collapse into stars. Perhaps the galaxy simply used up its supply faster than new gas could arrive. Each of these explanations leans on processes acting quickly and forcefully, which fits the wider theme of this story. Consider what the retired galaxy adds to the picture. The big wheel showed that order can arrive early. The wider census showed that order is common early. This galaxy shows that even the end of a galaxy's growth can arrive early. Birth, maturity, and retirement, all compressed into the universe's opening chapter. The standard growth chart had no room for a full life cycle unfolding that fast. The retired galaxy is small compared to the big wheel, with a stellar mass far below that of our own galaxy. That matters, because it means the fast life cycle is not limited to giants. Small systems can rush through their history too. It also raises the possibility that some of the clumpy, faint galaxies in early surveys are not young at all. They might be old, spent, and quiet, mistaken for newborns because nobody expected a retiree at that age. Astronomers have since found a handful of other early quiescent galaxies, enough to suggest this one is not unique, though the sample remains small. Each new example tightens the same question: how did the young universe run its clock so fast? And in searching for the answer, this telescope turned up a whole population of objects so strange that researchers still cannot agree on what they are. Scattered through the deepest images this telescope has taken, there is a population of objects that look like nothing astronomers have ever catalogued before. They appear as tiny, compact points of light, far smaller than a normal galaxy, and distinctly red in color. Researchers took to calling them little red dots, a casual nickname that stuck because nobody could agree on a more precise name for something they did not understand. They are common in early universe surveys, showing up at roughly the same era as the retired galaxy and the earliest rotating disks, and they are almost entirely absent from the nearby universe. Their red color could mean several very different things. Red light can come from older stars, from dust reddening younger stars, or from the hot, swirling gas around a growing black hole. Each interpretation leads to a wildly different conclusion. If the light comes mostly from stars, these objects would be absurdly dense, packing the stellar mass of a small galaxy into a region a few hundred light-years across, a density that nearby galaxies never reach. If the light comes mostly from black holes, those black holes would be far more massive, relative to their host galaxies, than anything seen today. Spectra of some little red dots show broad emission lines, a signature typically produced by gas moving at enormous speed near a black hole. That points toward the black hole explanation. Yet the same objects are surprisingly faint in X-rays, which growing black holes normally produce in abundance. That points away from it. Some researchers have proposed that these are black holes wrapped in unusually thick blankets of gas that muffle the X-rays. Others argue they are a new kind of extremely compact galaxy. A few suggest a mixture of both in a single object. This is a genuine, unresolved mystery, and it deserves that label without softening. The little red dots are confirmed to exist, confirmed to be common in the early universe, and confirmed to be rare later on. Everything about what they actually are remains open. Several research groups are currently arguing opposite positions in the published literature, which is exactly what an honest scientific mystery looks like from the inside. Why does this matter for the story of early spirals? Because if the little red dots are black holes far heavier than expected, they would show that black holes, like disks, reach maturity ahead of schedule, and black holes and galaxies grow together. A heavy black hole at the center of a young galaxy could shape how gas settles around it, either stirring it into chaos or, under the right conditions, helping to anchor a disk. Until the dots are understood, one possible piece of the early disk puzzle stays hidden. Picture the scale problem for a moment. A little red dot may hold as much mass as a small galaxy inside a region that would fit comfortably between our star and its nearest stellar neighbors. Whatever they are, they represent matter gathered into a tiny space at a speed the standard model struggles to produce. The dots hint that the early universe built heavy central objects quickly. The next chapter turns to the clearest evidence for that, a black hole so massive, so early, that its discovery required 2 telescopes working together to believe it. If disks grew up too fast, the black holes at their centers may have grown up even faster. Nearly every large galaxy, including our own, carries a massive black hole at its center. The standard picture holds that these black holes begin small, as the collapsed remains of the first massive stars, and then grow over billions of years by swallowing gas and merging with other black holes. There is a speed limit on that growth, set by the physics of infalling material, and under that limit, a black hole born early cannot become enormous quickly. This telescope, working alongside an orbiting X-ray observatory, found a black hole that appears to break that expectation. Its light left roughly 470 million years after the beginning, less than 4% of the universe's current age. The X-ray observatory caught the glow of superheated gas spiraling inward, the unmistakable fingerprint of an actively feeding black hole. The infrared telescope measured the distance and studied the host galaxy around it. The mass estimate came out at tens of millions of times the mass of our star. That alone is not shocking. What shocked researchers was the comparison with its host galaxy. The black hole appeared to hold a mass comparable to all the stars in the galaxy around it. In nearby galaxies, central black holes typically weigh in at a tiny fraction of a percent of the stellar mass. This one was closer to equal, a ratio that nearby galaxies never show. This is confirmed observation for the detection and distance, with the mass carrying meaningful uncertainty, as black hole masses at this distance always do. Even allowing for that uncertainty, a black hole this heavy, this early, cannot easily have started as the remains of a single star. There simply was not enough time for it to grow. That leads to an idea long discussed on paper and now taken far more seriously: heavy seeds. Instead of starting from a stellar corpse, some early black holes may have formed directly from the collapse of enormous clouds of gas, skipping the star stage entirely and beginning life already thousands of times heavier. This remains a theory. It has not been directly observed, but the overweight black hole found here matches what a heavy seed would be expected to produce, and researchers described it as the strongest evidence yet for that path. Consider how this connects to the disks. A galaxy's central black hole is not a passive passenger. When it feeds, it releases energy that heats and pushes gas throughout its host. Too much of that energy stirs the galaxy into chaos and shuts down star formation. Just enough, arriving in the right way, can regulate the flow of gas and help a disk settle into balance. If black holes were already heavy when their galaxies were young, that regulating influence would have been present from the start rather than arriving billions of years later. Picture the heart of a young galaxy under these conditions. A bar funnels gas inward, a heavy black hole at the center feeds on it and pushes back, The disk around them finds its balance far sooner than a galaxy with a tiny, slow-growing black hole ever could. That is a hypothesis rather than a finding, and it ties several strange threads of this story into one possible knot. And it raises the oldest question of all. Before galaxies, before black holes, before disks, there had to be the first stars. Nobody has confirmed seeing one, but the search has come closer than ever. Every star tonight is a descendant, and somewhere far back in time, there was a first generation with no ancestors at all. After the beginning, the universe spent a long stretch in darkness. It was filled with hydrogen and helium gas, cooling and spreading, with no stars anywhere to light it. Astronomers call this period the Dark Ages. It ended when gravity pulled the densest pockets of gas together tightly enough to ignite the first stars. That moment, cosmic dawn, is thought to have arrived somewhere between 100 and 200 million years after the beginning. Those first stars are known as population 3 stars, a name that comes from a numbering system in which our own star's generation is population 1. Theory predicts they were unlike anything shining today. Made only of hydrogen and helium, with none of the heavier elements that help modern gas clouds cool and fragment, they are expected to have been enormous, perhaps hundreds of times the mass of our star, blazing hot and short-lived. They would have burned through their fuel in a few million years and died in explosions that scattered the first heavy elements into space. Every heavier element in the universe traces back to those deaths. The carbon in your body, the oxygen you are breathing right now, the iron in your blood, all of it was forged inside stars and released when they died. The first generation started that chain. Without it, there would be no rocky planets, no water, and no one lying in a quiet room listening to a story about galaxies. Here is the honest state of the search. No population 3 star has ever been confirmed. They are predicted by theory with high confidence, but they lived so early and so briefly that catching their light directly pushes beyond even this telescope's reach. What this telescope has found are hints. In the outskirts of one of the earliest known galaxies, researchers detected a faint signature of helium glowing in a way that pristine, heavy element-free gas would produce. It is a tentative sign, and the team said so plainly, but it is the closest anyone has come. Why does cosmic dawn matter for the story of early spirals? Because the clock for building a galaxy starts ticking only once stars exist. If the first stars ignited earlier than expected, or if they seeded their surroundings with heavy elements faster than expected, then every galaxy that followed would have had a head start. Heavy elements let gas cool more efficiently, and cool gas is what settles into disks. A universe that seeded itself quickly is a universe that could build calm, flat, spinning galaxies quickly. Picture the first light, a handful of giant stars flaring to life inside vast, dark clouds, each one a beacon in a universe that had never been lit. Within a few million years, they were gone, and the elements they left behind began the slow work of building everything else. Those first stars did one more thing. Their light was strong enough to tear apart the hydrogen atoms surrounding them, beginning a process that would eventually clear a fog from the entire universe. And that clearing, as it happens, is something this telescope can actually watch. For its first several 100 million years, the universe was foggy, and the story of how that fog cleared is one this telescope can actually read in the light of ancient galaxies. After cosmic dawn, space was filled with neutral hydrogen, atoms with their electrons still attached. Neutral hydrogen is very good at absorbing a particular kind of ultraviolet light, the same light young, hot stars produce in abundance. So when the first galaxies lit up, much of their light was swallowed almost immediately by the surrounding gas. A distant observer would have seen them as dim, muffled smudges, their brightest light trapped close to home. That changed as those galaxies kept shining. Ultraviolet light carries enough energy to knock electrons off hydrogen atoms, turning neutral gas into charged gas, a process called ionization. Around every young galaxy, a bubble of cleared, transparent space began to grow. Over hundreds of millions of years, the bubbles expanded and merged until nearly all the hydrogen between galaxies had been stripped of its electrons, and the universe became transparent to that light. Astronomers call this stretch the epoch of reionization, and it is confirmed to have been essentially complete by about 1 billion years after the beginning. This telescope can measure how much fog surrounded a given galaxy by looking at how strongly its light was absorbed. Galaxies deep in the fog show a heavy cut in their spectrum. Galaxies sitting inside a cleared bubble show much less. By collecting many such measurements at different ages, researchers are building a map of how the fog thinned over time, region by region. That map has produced its own surprise, one that rhymes with everything else tonight. Some early galaxies appear to sit inside cleared bubbles far larger than their own light should have been able to carve. Either those galaxies were producing much more ionizing light than expected, or they had neighbors helping, or the process ran faster and earlier than the standard timeline allowed. All three possibilities remain under active investigation. Consider what a cleared bubble implies about the galaxy at its center. A galaxy that has already ionized a large volume around it has been shining brightly with many hot young stars for a substantial time. It is not a newborn, it has a history. When such a galaxy also shows an organized disk, the two findings support each other. A galaxy old enough to clear its surroundings is a galaxy that has had time, at least on the compressed clock this story keeps returning to settle. Reionization also matters for the gas that feeds galaxies. Once the gas between galaxies is ionized and heated, it becomes harder for the smallest galaxies to pull it in. The larger galaxies keep growing while the smallest ones are starved. That sorting may help explain why the early universe holds both fast-growing giants like the Big Wheel and countless faint fragments that never got the chance to become anything more. Picture the young universe near the end of this period. Bubbles of clear space swelling outward from thousands of bright galaxies, merging like drops of water spreading on paper, until the last pockets of fog vanish and the whole cosmos opens to view. Everything this telescope sees from that point onward travels through transparent space. The galaxies clearing that fog were the brightest of their era, and a few of them hold the record for the most distant objects ever confirmed. Their light is so old that when it left, the universe had barely begun to keep time. Every telescope generation has a most distant galaxy, and this one has pushed that record into a territory that was supposed to be empty. For years, the record belonged to a galaxy found by an older space telescope, catalogued under a survey name, whose light left roughly 400 million years after the beginning. It was unusually bright for its age, bright enough that astronomers debated whether its distance estimate could really be right. This new telescope settled the question with a detailed spectrum, confirming the distance, and then found the galaxy was even stranger than expected, with hints of a growing black hole and unusually rich chemistry for something so young. Then the record fell again. In deep survey images, researchers identified a galaxy whose light left just under 300 million years after the beginning, when the universe was about 2% of its present age. A spectrum confirmed it. This is confirmed observation, and it currently stands as the most distant galaxy whose distance has been verified in detail rather than estimated from colors alone. Consider that figure, 2%. On the imagined 100-year human lifetime used earlier tonight, this galaxy was already shining, already several hundred light years across, already holding hundreds of millions of times the mass of our star in stars, before that lifetime reached its second birthday. And it was bright, far brighter than the standard growth chart predicted any galaxy at that age could be. Brightness is the crux. A galaxy's light comes mostly from its stars, so a brighter galaxy generally means more stars, or more massive stars, or stars formed more efficiently. Under the standard model, a galaxy at 2% of the universe's age should still be gathering its first gas, barely lit at all. Instead, this one glows with a luminosity that models had reserved for galaxies hundreds of millions of years older. Researchers have been careful about what this does and does not mean. The distance is confirmed, the brightness is confirmed, the interpretation is open. Perhaps early stars formed with a heavier average mass, so fewer stars produced more light. Perhaps star formation ran with almost no breaks in these first galaxies, converting gas to stars far faster than nearby galaxies manage. Perhaps some of the light comes from a hidden black hole. Each explanation is being tested against the growing sample of confirmed record holders. Notice how this connects to the disks. The same three candidate explanations, heavier stars, weaker breaks, and hidden black holes, appear again and again across every early universe puzzle tonight. The spiral problem and the brightness problem may be two symptoms of one underlying cause. An early universe that converts gas into structure with a speed and efficiency the standard model never anticipated. Astronomers expect the record to fall again. Candidates whose colors suggest even earlier ages are already in the queue for spectroscopic confirmation. Each one that holds up pushes the moment of first light closer to the beginning and squeezes the available time for galaxy building tighter still. Yet light, for all it reveals, shows only the visible part of a galaxy. Beneath every disk, every bar, every bright early beacon, there is a scaffold of matter that emits no light at all, and the story of fast galaxies may ultimately be a story about that invisible frame. Before any galaxy can settle into a disk, something has to hold the gas in place, and in the standard picture that something cannot be seen. Dark matter is the name astronomers give to matter that produces gravity, but neither emits nor absorbs light. Its existence is inferred from the way galaxies rotate, the way clusters bend light, and the pattern of the earliest radiation in the universe. Those lines of evidence agree well enough that dark matter is treated as confirmed in the sense that its gravitational effects are measured, even though its actual nature remains a genuine unknown. In the standard model, dark matter takes the lead in building structure. It began clumping under gravity long before ordinary gas could, because gas was still hot and pushed outward by pressure, while dark matter felt only gravity. Those early clumps, called halos, grew by pulling in more dark matter and by merging with one another. Ordinary gas then fell into the gravitational wells the halos had already dug. Every galaxy, in this picture, sits inside a halo many times larger and heavier than the visible galaxy itself. Picture a halo as an invisible bowl. The gas is water poured into that bowl. How the water settles depends on the shape of the bowl, how quickly it was carved, and how often something jostles it. A bowl that forms early and stays steady lets the water settle flat. A bowl that keeps changing shape as it merges with other bowls keeps the water sloshing. The standard growth chart assumed early bowls were constantly being jostled. Here is where the early disks press on the model. A galaxy with a flat rotation curve, like the big wheel, is a galaxy whose halo is already deep, steady, and roughly symmetrical. For the halo to be that settled so early, either halos assembled faster than the standard simulations predicted, or galaxies can hold a disk together even while their halos are still growing, or the connection between halo growth and disk growth is looser than assumed. Each of those possibilities is being tested in updated simulations. There is a related measurement worth noting. Astronomers can estimate how much of a galaxy's total mass is in stars versus how much sits in its halo. For nearby galaxies, stars typically make up only a small fraction. For some early galaxies, the stellar mass appears to be a surprisingly large fraction of what the halo should hold, as if these galaxies converted their available gas into stars with unusual efficiency. That again points toward the same theme, the early universe turning raw material into finished structure faster than expected. None of this challenges the existence of dark matter itself. The measurements of gravity are as solid as ever. What is being questioned is the timing and efficiency of what happens inside the halos, the physics of gas and stars, rather than the physics of the invisible frame. So the scaffold appears to have been in place early. The next question is how gas got into it so gently, because there are two ways for material to arrive at a young galaxy, and only one of them leaves a disk intact. There are two ways to deliver gas to a growing galaxy, and they lead to two entirely different kinds of galaxy. The first way is the one the standard growth chart emphasized. Gas falls into a halo from all directions, collides with gas already there, and heats up in a shock. Hot gas resists settling. It has to cool slowly, radiating away its energy over long stretches of time before it can sink into a disk. This hot mode of accretion is naturally slow, and it is one of the main reasons the old timeline for disk building ran into billions of years. The second way was proposed on paper and later seen in simulations. In the early universe, the web of dark matter has a shape, with dense filaments stretching between halos like threads in a net. Gas flows along those filaments. When it reaches a halo, it can arrive as a narrow, dense stream that punches through the hot surrounding gas without shocking, delivering cold material straight toward the galaxy's center. This is called cold mode accretion, and astronomers often describe it as rivers of cold gas. Picture the difference. Hot mode is like rain falling evenly on a lake and slowly warming it. Cold mode is like a mountain stream pouring directly into the lake, cold, focused, and carrying momentum in a particular direction. A stream arriving with momentum adds rotation. Several streams arriving from different filaments can combine into a single steady spin. In that picture, a galaxy fed by cold rivers does not have to wait for its gas to cool. It arrives cool, and it arrives already turning. Simulations that include cold streams routinely produce rotating disks earlier than simulations that do not. That is not a fringe result, it is a consistent feature of modern galaxy models. The open question is not whether cold streams exist in those models, but how dominant they were in the real early universe, and whether they can deliver enough gas, gently enough, to build something as massive and calm as the Big Wheel by 2 billion years. Observational evidence is growing but incomplete, and it deserves an honest label. Astronomers have detected faint glowing filaments of gas connecting to distant galaxies using instruments sensitive to the glow of hydrogen. Those detections confirm that filaments exist and that gas moves along them. Measuring exactly how much gas flows in and at what temperature remains at the edge of what current instruments can manage. So cold streams are a strong, well-supported candidate rather than a confirmed, complete explanation. There is a subtle point that makes this idea especially attractive. Cold streams should be most effective in the early universe, when the web of filaments was denser and gas was more abundant, and should fade in importance later as halos grow hotter and more massive. That would mean the fast path to a disk was open early and closed later, which fits the observed pattern of early disks arriving on an accelerated clock and nearby galaxies following the slower, familiar one. Fed gently by cold rivers, a galaxy could form stars rapidly. But rapid star formation comes with a problem. Stars, once born, push back, and the strength of that pushback may be the single most important unknown in this entire story. Every galaxy carries its own braking system, and one of the leading ideas about the early universe is that, for a brief window, the brakes did not work. When a massive star forms, it does not sit quietly. It blasts its surroundings with intense radiation and powerful winds, and after a few million years it explodes, hurling gas outward at enormous speed. In a typical galaxy, that energy heats and scatters the surrounding gas, slowing the birth of the next generation of stars. Astronomers call this feedback. It is the reason nearby galaxies convert only a small fraction of their gas into stars each cycle instead of using it all at once. Feedback is built into every modern galaxy simulation, and its strength is one of the most sensitive settings in those models. Turn it up, and galaxies form stars sluggishly. Turn it down, and they form stars in bursts. For decades, the strength was tuned to match nearby galaxies, and that tuning produced the slow timeline the standard growth chart relied on. A newer idea suggests that in the densest early galaxies, the timing simply did not allow feedback to kick in. Gas in those systems was so dense that it collapsed into stars in less time than it takes a massive star to reach the end of its life and explode. By the time the first supernovae went off, most of the surrounding gas had already become stars. The breaks were still there. They just arrived too late to matter. Researchers describe this as feedback-free star formation, and it remains a theoretical proposal under active testing. Consider what that would mean. A galaxy in that regime could convert nearly all its available gas into stars in a single rapid burst, producing far more light and far more stellar mass than the standard model predicts for its age. That matches the overly bright record holders. It matches the retired galaxy that formed its stars in one brief burst and then shut down. And it may match the heavy early disks, which seem to hold more stars than their halos should have allowed. There is a second part of the braking system, the central black hole. When it feeds, it releases energy that can heat gas across the entire galaxy. In the nearby universe, black hole feedback is thought to be the main reason massive galaxies eventually stop forming stars. In the early universe, with black holes apparently heavy from the start, this break may have been present sooner, which could explain how some galaxies both grew fast and stopped fast. Picture two breaks on a runaway cart. The first, from exploding stars, is slow to engage. The second, from the black hole, slams on hard once it engages. A young galaxy that raced downhill before the first break caught, then got stopped abruptly by the second, would look exactly like the compressed life cycles this story keeps finding. This remains hypothesis rather than confirmed physics, but it has a testable consequence. Galaxies that formed stars without breaks should have left behind a specific chemical fingerprint in their gas, and reading that fingerprint depends on seeing through something that has blocked astronomers' view for as long as they have looked at distant galaxies. Between every distant galaxy and the telescope watching it, there is dust, and dust has quietly shaped nearly every conclusion in this story. Cosmic dust is made of tiny grains of carbon, silicon, and other heavy elements, each grain far smaller than the width of a hair. It forms in the outflows of dying stars and in the debris of stellar explosions. Because it is made of heavy elements, dust can only exist once stars have lived and died, so its presence in a galaxy is itself a kind of clock. A dusty galaxy is a galaxy with a history. Dust does two things to light. It absorbs shorter wavelengths, the blue and ultraviolet light of young stars, dimming and reddening the galaxy as seen in visible and near-infrared light. And it re-emits that absorbed energy at much longer wavelengths, glowing faintly in the far infrared and millimeter range. A galaxy can therefore look faint or even invisible in one kind of light while shining in another. This matters enormously for early galaxies. The infrared telescope at the heart of this story sees starlight. The radio array in the Chilean desert sees dust glow and cold gas. Neither sees everything. A galaxy heavily wrapped in dust can be nearly missed by one and obvious to the other. That is one reason cross-checks between the two instruments carry such weight, and one reason early galaxy counts remain uncertain. Dust also complicates the brightness puzzle. If early galaxies had less dust than expected, more of their blue starlight would escape, making them appear brighter without needing extra stars. Some measurements support this, showing early galaxies bluer than models predicted. Others have found surprisingly dusty systems at similar ages, galaxies already rich in the products of dead stars. Both results are confirmed for the specific galaxies studied, and together they show that early galaxies were not all alike. Consider what a dusty early galaxy implies. Dust means dead stars. Dead stars mean at least one full generation has already run its course. A galaxy with plenty of dust at 1 billion years has been forming stars, watching them die, and recycling their remains long enough to build a substantial reserve. That is the same compressed history seen in the disks and the retired galaxy, written in a different language. Dust carries one more clue: the mix of heavy elements in a galaxy's gas, which astronomers call its metallicity, records how many generations of stars have enriched it. Several early galaxies show metallicities far higher than the standard model predicted for their age, which is exactly what a rapid, break-free burst of star formation would leave behind. The chemical fingerprint mentioned in the last chapter is readable, and in some galaxies, it points toward fast, early enrichment. Picture a galaxy at 1 billion years, its bright blue disk wrapped in a thin veil of ash from stars that have already lived and died. That ash is the residue of a history that the standard timeline said had not happened yet. Every idea in the last few chapters, cold rivers, failing brakes, early dust, lives inside computer models before it is ever tested against the sky. And those models, built and rebuilt in some of the most powerful machines on Earth, are where the real argument over the early universe is now being fought. Astronomers cannot run experiments on galaxies, so they build them instead inside machines and watch what happens. A modern cosmological simulation begins with a box of space, often hundreds of millions of light years on a side, filled with a nearly uniform mix of dark matter and gas as it existed shortly after the beginning. Tiny ripples in that mix, matching the pattern observed in the earliest light of the universe, are added as seeds. Then the simulation lets gravity, gas physics, cooling, star formation, and feedback act together, step by step, across more than 13 billion years of simulated time. At the end, the box is full of galaxies, and researchers compare them with the real sky. These simulations have been remarkably successful. They reproduce the overall web of galaxies, the range of galaxy masses, the way galaxies cluster, and the general split between spirals and ellipticals in the nearby universe. That success is why the standard growth chart earned so much trust. It was not a guess. It was the output of models that matched almost everything astronomers could check. Almost everything. The one place where the simulation struggled was the early universe, and that was hard to notice until this telescope arrived. Older simulations, asked to produce galaxies at 2 billion years, delivered mostly clumpy, merging, unsettled systems, exactly as the growth chart described. They produced few large disks and almost no barred spirals. Compared with the big wheel, the barred spiral, the twin of our own galaxy, and the wider census, the simulated early universe looks too messy. The response has been a burst of activity. Research groups are rerunning their models with adjustments, testing what it takes to produce early disks. Some raise the efficiency of star formation in dense gas. Some weaken early feedback. Some improve how cold streams are handled by increasing resolution, so narrow filaments survive instead of being smeared out. Some add heavy black hole seeds. Each adjustment is then checked against every other observation, because a change that fixes early disks while breaking the nearby universe is no fix at all. Consider the scale of this work. A single high-resolution simulation can take months on a machine with tens of thousands of processors. Changing one setting and rerunning it is not a quick test. Progress comes from many groups, running many variations and comparing notes, a slow, careful, worldwide process of elimination. Some updated simulations now do produce disks by 2 billion years, and a few produce bars. That is encouraging, and it is also a warning. A model that can be tuned to produce any outcome has stopped being predictive. The real test is whether an adjusted model, tuned to match the big wheel, then correctly predicts something it was not tuned for, such as how common early disks should be at even earlier ages. Those predictions are being made now, and the next surveys will judge them. Picture a room full of small universes, each running under slightly different rules, each being held up against the real sky to see which one matches. Somewhere among them is a rule set that produces both the big wheel and our own galaxy. Finding it is the work of the coming decade. And our own galaxy, it turns out, has been keeping its own record of how fast it grew up, written in the ages and motions of its stars. Reading that record has become possible only in the last few years. The closest evidence that galaxies grow up fast is not in a distant survey. It is overhead tonight, in the stars of our own galaxy. For most of the history of astronomy, the age of our galaxy's structure was a rough estimate. That changed with a space observatory built for a single purpose: to measure the positions, distances, and motions of more than 1 billion stars with extraordinary precision. Combined with ground-based surveys that read the chemistry of hundreds of thousands of stars, this dataset lets astronomers assign approximate ages to individual stars and trace how our galaxy assembled itself, layer by layer. Our galaxy has 2 main disks, one nested inside the other. There is a thin disk where our star lives, holding most of the younger stars and the spiral arms. And there is a thicker, puffier disk surrounding it, made of older stars moving on more tilted, energetic orbits. The thick disk is the older structure, and its age tells astronomers when our galaxy first settled into something disk-shaped. The result, published after careful peer review, is confirmed and striking. The thick disk began forming roughly 13 billion years ago, within about 800 million years of the beginning of the universe. Our own galaxy, in other words, started building a disk when the universe was around 6% of its current age. That is the same era as the earliest rotating disks found by the radio array, and earlier than the big wheel. Consider what that means for tonight's story. The galaxy you are lying inside did not wait billions of years to organize itself. It began early, in the same accelerated window that this telescope has been revealing across the distant universe. The big wheel is not an alien exception. It is a distant relative, doing early what our own galaxy was also doing early. The stellar record shows something else. Around 10 billion years ago, our galaxy swallowed a smaller galaxy in a major merger. Astronomers found the debris of that collision as a population of stars still sharing a distinctive set of orbits, a fossil of the event. That merger stirred up the young disk, thickened it, and delivered a large amount of fresh gas. Afterward, the thin disk began forming in earnest, building up the calm, flat structure that carries our star today. Here is the subtle part. That merger was a wrecking ball of exactly the kind the standard growth chart described, and yet our galaxy came through it with a disk intact, thickened rather than destroyed. Then it rebuilt a thinner disk on top. Rather than erasing order, the collision reshaped it. That single fact, read from stars in our own sky, suggests the wrecking ball effect is less absolute than the old chart assumed. Picture our galaxy at 1 billion years old, a modest, thick, spinning disk, already turning, already gathering stars, in a universe still lifting its fog. It would have looked much like the smaller early disks found in the distant surveys tonight. Somewhere in the same universe, a few billion light years away, the big wheel was building itself on a larger scale. The lesson from our own galaxy is that disks can survive what should destroy them. Whether that holds for other galaxies, and under what conditions, is a question astronomers have taken directly to the simulations, with results that reshape the meaning of a galactic collision. Earlier tonight, a collision was described as a wrecking ball that erases spiral structure. That is true for some collisions. It turns out to be false for others, and the difference matters. In the standard picture, when 2 galaxies of similar size merge, their stars are flung onto random orbits and their disks are destroyed, leaving behind a round, jumbled, elliptical galaxy. That picture came from simulations of nearby galaxies, which are mostly made of stars with relatively little gas. Stars do not collide with each other during a merger. They pass through and scatter. Once scattered, they have no way to settle back into a disk. Gas behaves differently. Gas clouds do collide. When two gas-rich galaxies merge, their gas crashes together, loses energy, and sinks toward the center of the combined system. As it sinks, it conserves its rotation and settles into a new disk. If enough gas is present, that new disk can be large enough to dominate the merged galaxy, and new stars born inside it form a fresh spiral. Simulations of gas-rich mergers show this clearly, and the result is confirmed in the models even if catching it in the act remains difficult. Here is the key. Early galaxies were far richer in gas than nearby ones. In the first few billion years, gas often made up half or more of a galaxy's ordinary matter, compared with a small fraction today. So, a merger at 2 billion years was not the same event as a merger today. It was a collision of gas clouds more than a collision of star systems, and gas clouds, when they collide, rebuild disks. Consider what this does to the paradox. The standard growth chart said the early universe was a demolition derby, and it was right. Collisions were frequent, but the chart assumed each collision left wreckage, and that assumption came from studying collisions between the wrong kind of galaxy. Gas-rich collisions can leave behind a disk, sometimes a larger one than either galaxy had before. The demolition derby may have been building wheels rather than breaking them. There is a limit, and it deserves stating. A merger that delivers gas from a direction opposite to the existing rotation can cancel spin rather than add to it. A merger that triggers a violent burst of star formation and black hole feeding can blow the gas out before it settles. So, not every early collision builds a disk. The outcome depends on gas content, geometry, and timing, which is why the early universe holds both organized disks and chaotic clumps side by side. This idea connects directly to the discovery that opened tonight's story. The Big Wheel is enormous, far larger than most galaxies of its era, and it sits in a crowded region where collisions would have been common. If gas-rich mergers build disks, then a galaxy in a busy neighborhood, fed by repeated gas-rich collisions, could grow both large and orderly at once. Its size and its order would come from the same source rather than being in tension. Picture two young, gas-heavy galaxies drifting together. Their gas meets, flares, and pours toward a common center. Out of the collision, a wider disk forms, spinning faster than either had before. Seen a few 100 million years later, it would look like a single galaxy that had grown up impossibly fast, which brings the story back to the Big Wheel's neighborhood, a place that turns out to be one of the most crowded regions astronomers have found at that age. Where a galaxy grows up may matter as much as when, and the Big Wheel grew up in a very unusual place. When researchers first measured the Big Wheel's distance, they also mapped the galaxies around it. The region turned out to be far denser than average, a crowded gathering of galaxies at the same distance, clustered around the bright quasar whose light had first drawn attention to the field. Astronomers call such a region a protocluster, the early stage of what will eventually become a galaxy cluster, one of the largest gravitationally bound structures in the universe. This is confirmed observation. The Big Wheel was not floating alone in a quiet pocket of space. It sat in one of the busiest environments of its era, surrounded by neighbors and threaded by the dense filaments of gas that feed such regions. At first, this seems to deepen the paradox. A crowded region should mean more collisions, more disruption, and less chance for a calm disk to survive. Under the standard growth chart, a protocluster is the last place to look for an orderly spiral. Yet here was the most orderly spiral of its age, sitting right in the middle of one. The research team proposed that the crowding may actually have been the cause rather than an obstacle. A protocluster is where the cosmic web is densest, which means gas filaments converge there. A galaxy at that convergence receives gas from multiple streams at once, arriving cold and fast, and if gas-rich collisions with neighbors rebuild disks rather than destroying them, then a crowded neighborhood provides both abundant fuel and repeated opportunities to grow. Under that view, the Big Wheel's environment is exactly why it became so large so quickly. This proposal is a hypothesis, and the team framed it as one. Testing it requires finding more early disks and checking whether they too tend to live in dense regions. Early results from other surveys are mixed. Some large early disks sit in crowded fields, others appear more isolated. The sample is small and the question remains open. Consider the two competing pictures. In the first, calm environments let disks settle undisturbed, and the fast disks are the lucky ones that avoided traffic. In the second, busy environments feed disks aggressively, and the fast disks are the ones that got the most fuel. These predict opposite things about where early spirals should be found, which makes the question answerable. A future survey mapping the environments of a few hundred early disks could settle it. There is a quieter implication in the big wheel's address. Protoclusters eventually collapse into galaxy clusters, dense cities of galaxies where mergers are constant and gas is heated by the cluster's own gravity. Galaxies that fall into such cities usually lose their disks over time and become ellipticals. So the big wheel, for all its early beauty, was probably not destined to stay a spiral forever. Picture the region as it was, a bright quasar blazing at the center, dozens of young galaxies drifting toward it along invisible threads, gas pouring inward from every direction, and the big wheel, wide and calm, turning steadily in the middle of it all. To see galaxies in regions like this at all, astronomers often need help from the universe itself, a natural magnifying glass made of gravity that has turned the faintest early galaxies into objects this telescope can study. Some of the most detailed views of early galaxies come from looking through something else entirely, a wall of mass so heavy that it bends light like a lens. Mass warps the space around it, and light follows that warp. When a massive galaxy cluster sits between us and a more distant galaxy, the cluster's gravity bends the distant galaxy's light around it, stretching and brightening the image. Astronomers call this gravitational lensing. It was predicted by the theory of general relativity and has been confirmed thousands of times. A strong lens can magnify a background galaxy by a factor of 10 or more, and sometimes far beyond. That magnification is a gift. A galaxy too faint and too small for direct study becomes bright enough to measure and large enough to resolve. Many of the deepest early universe surveys deliberately target the sky behind massive clusters for exactly this reason, using the cluster as a free extension to the telescope. Lensing gave astronomers one of the most striking early disks found before this telescope launched. The Radio Array in Chile studied a galaxy whose light left about 1.5 billion years after the beginning, lensed by a foreground galaxy into a near-perfect ring of light. By mathematically undoing the lens, researchers reconstructed the galaxy's true shape. It was a calm, rotating disk with a central bulge and orderly motion, remarkably similar in structure to our own galaxy, though without visible spiral arms. This is confirmed observation, and the team described it as unexpectedly mature for its age. Consider what the ring revealed. The reconstruction showed gas moving with very little random motion, a cold and settled disk in an era when the standard growth chart predicted turbulence. It was another early warning, like the Wolf disk, that orderly structure was forming ahead of schedule, delivered years before the infrared telescope began finding early spirals routinely. Lensing has a price. Undoing the lens requires a precise model of the mass in the foreground, and dark matter, being invisible, makes that model uncertain. Small errors in the lens model can distort the reconstructed galaxy. Researchers guard against this by testing many lens models and reporting only features that survive all of them. Even so, lensed results carry an extra layer of caution compared with direct images. There is a second gift in lensing beyond magnification. Because light takes different paths around a lens, the same galaxy can appear in several places on the sky at once, and the light arriving along each path takes a slightly different amount of time. If the galaxy changes, such as a star exploding inside it, the change appears in each image at a different moment. That delay lets astronomers measure distances in a way independent of every other method, providing a cross-check on the cosmic timeline itself. Picture a galaxy at 1.5 billion years, its light sweeping past a massive cluster, bending, stretching, and arriving at Earth as a glowing ring. Inside that ring, unfolded by careful mathematics, sits a calm disk that should not exist yet. Lensed or direct, all of these early disks sit in the run-up to a particular era, the busiest period in the history of star formation, when the universe was building stars faster than at any time before or since. If the history of the universe were a single day, there would be one stretch of it, late morning through early afternoon, when the lights came on brightest. Astronomers have measured how quickly stars formed across cosmic history by counting galaxies at every distance and adding up their light. The result is one of the most reliable curves in the field. Star formation ramped up steeply in the first 2 billion years, peaked around 3 to 4 billion years after the beginning, then declined steadily to the present day. That peak is called cosmic noon. Roughly half of all the stars that exist today were formed in the few billion years around it. The big wheel, at 2 billion years, sits just before cosmic noon. The barred spiral sits in the same window. The earliest rotating disks sit well before it, on the steep climb. In other words, the organized galaxies found tonight were built while the universe was still ramping up toward its most productive era, rather than at or after the peak, when the standard chart would have expected them. Consider why the ramp-up matters. During that climb, gas was abundant, halos were growing fast, cold streams were at their strongest, and mergers were frequent and gas-rich. Every ingredient that the last several chapters described as favoring rapid disk formation was present in abundance. Cosmic noon was the payoff of that build-up, and the early disks are evidence that the payoff began earlier than the curve alone would suggest. The decline after noon carries its own lesson. As the universe expanded, gas thinned out, halos heated, and cold streams faded. Galaxies increasingly relied on their remaining reserves. Star formation slowed everywhere, and the age of rapid disk building gave way to an age of slow maintenance. Our own galaxy today forms only a few new stars per year, a trickle compared with the torrent of cosmic noon. This is confirmed history, assembled from decades of surveys, and it frames the whole paradox in a helpful way. The universe had a fast phase and a slow phase. The standard growth chart was calibrated mostly against galaxies in the slow phase, the nearby universe, and then extended backward into the fast phase. The early disks are the fast phase pushing back, insisting that rules learned in the slow era do not fully apply. There is a detail in the star formation curve that connects to the record holders. The steep early climb is steeper than older models predicted, with more light arriving from earlier ages than the standard chart allowed. That is the brightness puzzle again, now seen as a feature of the entire universe rather than a handful of unusual galaxies. Everything early was doing more, sooner. Picture the universe at cosmic noon. Galaxies everywhere are ablaze with new stars. Disks are wide and bright. Bars are funneling gas inward. Black holes are feeding. And the sky, if anyone had been there to see it, would have been crowded with light. Then, slowly, the tide goes out. Finding galaxies from before that noon required a way of looking that seemed almost absurd when it was first proposed, pointing a great telescope at an apparently empty patch of sky and simply waiting. The strategy that revealed the early universe began as a decision that many astronomers considered a waste of precious telescope time. In the middle of the last decade of the 20th century, the director of a major space telescope program chose to spend a large block of his personal observing allocation on a patch of sky chosen because it contained almost nothing. No bright stars, no known galaxies, just a dark spot far from the plane of our galaxy. The telescope stared at it for 10 consecutive days, collecting light photon by photon. The result changed the field. Inside that seemingly empty patch, roughly the size of a grain of sand held at arm's length, the final image showed thousands of galaxies, many of them so distant that their light had been traveling for most of the age of the universe. It was called a deep field, and it demonstrated that the early universe was not out of reach. It was simply faint, and faintness can be beaten with patience. The method is simple in principle. Point at a dark spot. Keep collecting. Every additional hour adds a little more light from the faintest sources, and the noise averages down while the signal builds up. Given enough time, galaxies that are billions of times fainter than anything the eye could see become measurable. Later deep fields pushed the exposure to weeks, and each one reached further back than the last. This telescope inherited that strategy and improved on it in two ways. Its mirror is far larger, gathering more light per hour, and it sees in infrared, which matters because the expansion of the universe stretches the light of distant galaxies into infrared wavelengths. A galaxy that emitted blue light 2 billion years after the beginning arrives at Earth as infrared. The older telescope, working mainly in visible light, could see only the earliest galaxies' faintest edges. This one sees them directly. Consider how the survey that found the wider census of early disks, the record holding distant galaxies, and the twin of our own galaxy all trace back to this approach. Each was a deep field, or a survey built on deep field principles, pointed at a region chosen for having little in the way. Even the big wheel, found near a quasar rather than in an empty field, was caught in a long exposure of the kind deep fields taught astronomers to take. There is a subtle bias in deep fields that researchers work hard to correct. A deep field is a narrow window. It samples a tiny volume of the universe, and if that volume happens to contain an unusual region, a protocluster or a void, the results can mislead. This is why several separate fields are always compared, and why the discovery of early disks in multiple independent fields carries more weight than any single image. Picture the very first deep field image. Astronomers who had expected a mostly blank frame, staring at a screen crowded with galaxies of every shape and color, some of them tiny red specks that turned out to be among the most distant objects ever recorded. That moment, more than any single discovery, opened the door to everything tonight has covered. Every deep field is a bet on what lies beyond the current limit, and the next generation of instruments is being built to make that bet on a far larger scale. Every open question tonight has the same practical answer. Look further, look wider, and look more carefully, and the tools to do that are already being assembled. The infrared telescope at the center of this story has years of operation ahead of it, and its schedule now includes long programs aimed squarely at early disks. Some will revisit the big wheel and its neighbors with longer exposures to map their rotation in finer detail. Others will target the twin of our own galaxy to confirm its distance with a spectrum. Others still will search for the bar hinted at in the earliest rotating disk. The questions raised in the first few years of observing are becoming the observing plan for the next several. A second space observatory, built with a mirror comparable in size to the older visible light telescope, but with a field of view roughly 100 times wider, is designed to survey enormous areas of sky in infrared. Where this telescope studies small fields in depth, that one will map the sky in breadth. It will resolve early disks in less detail, yet it will find candidates by the thousands, turning a handful of examples into a population large enough to test whether early spirals prefer crowded regions or quiet ones. On the ground, an extremely large telescope is under construction in the Chilean desert, with a primary mirror nearly 130 feet across, several times wider than any optical telescope operating today. Its resolving power, combined with instruments that correct for the blurring of Earth's atmosphere, is expected to reveal structure inside early galaxies at a level of detail currently reserved for nearby ones. Spiral arms, bars, and central bulges at 2 billion years could become routine measurements rather than remarkable ones. A new survey telescope in the same mountains has begun scanning the entire visible sky every few nights, building a decade-long movie of everything that changes. Its main targets are nearer, but its catalogue of lensing clusters and its census of galaxies across billions of light-years will feed target lists for every other instrument tonight has mentioned. The radio array continues to expand its capabilities as well, with upgrades planned to sharpen its view of cold gas and dust in the earliest galaxies. Since it sees what the infrared telescope cannot, every improvement there tightens the cross-check that has already proven so valuable. Consider what these instruments together could deliver within a decade. A confirmed count of how many disks existed at every age back to the first few 100 million years. A map of where those disks lived. Rotation curves for dozens of them. Chemical fingerprints revealing how fast they formed their stars. And a direct comparison between all of that and the updated simulations, settling which adjustments to the standard growth chart were right. This is planned work rather than completed work, and plans in astronomy slip, but the direction is set. The field has moved from asking whether early disks exist to asking how common they are, how they formed, and what they mean for the timeline of everything. Picture the coming years. Several telescopes, on Earth and above it, all pointed at the same stretch of cosmic history, comparing notes, each filling a gap the others cannot. The big wheel, found by chance, has become the target of a deliberate search. As that search proceeds, a natural worry arises for anyone following along. If the standard timeline for galaxies was wrong, what else might be wrong? The next chapter faces that question directly. When a prediction fails as clearly as the growth chart failed, it is fair to ask whether the whole framework behind it is in trouble. The honest answer is no, and the reasons matter. The standard model of cosmology rests on a small number of pillars. The universe began in a hot, dense state and has expanded ever since. Its expansion history and its large-scale structure are governed by gravity acting on dark matter, ordinary matter, and a form of energy driving accelerated expansion. Tiny ripples in the earliest light grew, under gravity, into the web of galaxies seen today. Each pillar is supported by multiple independent measurements, and none of them is challenged by early spirals. What early spirals challenge is a different layer. Sitting on top of the cosmological framework is a set of assumptions about what happens inside dark matter halos, how gas cools, how quickly stars form, how strongly they push back, how black holes grow, how mergers reshape disks. Astronomers call this baryonic physics, the physics of ordinary matter, and it is by far the messiest and least certain part of any simulation. The growth chart was built from that layer. The failure is in that layer. Consider an analogy. Imagine a well-tested map of a coastline that also includes an estimate of how long it takes to walk between towns. If travelers keep arriving hours earlier than the estimate, the coastline is not wrong. The walking speed assumption is, early disks are travelers arriving early, the coastline, the underlying structure of the universe, is unchanged. This is why researchers have responded by adjusting the physics of gas, stars, and feedback, rather than questioning dark matter or the expansion history. Those adjustments are constrained tightly, because any change must still reproduce the nearby universe, the star formation curve, the earliest light, and everything else the model already gets right. The room for adjustment is real but narrow, and finding a set of rules that fits both the early disks and everything else is the hard problem now underway. There is an important caution in the other direction. Science does not protect a model by refusing to question it. If future surveys find organized galaxies at ages where even the most generous baryonic physics cannot produce them, the questioning would have to move down a layer toward the timing of halo assembly itself. That would be a far bigger change. Nothing observed so far requires it. Several researchers have said so directly, and some have also said they are watching for it. Mark the trust signals clearly. The existence of early disks is confirmed. The failure of the old growth chart's timeline is confirmed. The specific fix is unknown, with several candidates under test. The underlying cosmological framework is unchallenged by current evidence, and the possibility of a deeper revision remains open, contingent on what the next generation of surveys finds. Picture the model as a building with a solid foundation and several floors above it. The early disks have shown that the wiring on one floor was installed on the wrong schedule. The electricians are at work. The foundation has not moved. With the framework intact, one question remains about the galaxy that started this story. It was seen as it was nearly 12 billion years ago. What has become of it since? The big wheel seen tonight is a snapshot from the deep past, and the galaxy itself has had almost 12 billion years to change since that light left. Astronomers cannot watch a single galaxy age. Instead, they compare galaxies at different eras and use simulations to connect them, tracing the likely future of a system like the big wheel by following similar systems forward in the models. The answer those models give is consistent and a little melancholy. A galaxy as massive as the big wheel, sitting in a protocluster, does not stay a calm spiral. Over the following billions of years, the protocluster collapses into a full galaxy cluster. The gas between galaxies heats to millions of degrees, so hot that it can no longer cool and fall into disks. Galaxies in the cluster core lose their supply of fresh gas and stop forming stars. Repeated mergers with neighbors, now poor in gas and rich in stars, scatter their disks. The likely end state is a giant elliptical galaxy, enormous and red, dominated by old stars, sitting near the center of a cluster. Consider what that means. The big wheel was probably a spiral for only a fraction of its life. Its disk, so remarkable at 2 billion years, may have been dismantled by 5 or 6 billion years. The order that astronomers found so hard to explain was likely temporary, a stage in the life of a galaxy destined to become something very different. That does not lessen the puzzle, it sharpens it. The universe built a full spiral quickly, and then, in the same crowded environment, took it apart again. This is a projection from models rather than an observation, and it deserves that label. No one has seen the big wheel's descendant, but giant ellipticals at the centers of nearby clusters are confirmed to exist in abundance, and their stars are confirmed to be old, with ages that reach back to the era when the big wheel was spinning. Somewhere in the present-day universe, there are cluster galaxies whose oldest stars formed inside disks like it. There is a striking connection to the retired galaxy from earlier tonight. That small system stopped forming stars at 700 million years. The big wheel, on this projection, would stop much later, but for related reasons. The loss of cold gas, whether by feedback, by heating, or by exhaustion. Every galaxy's story has the same final chapter, only the timing differs. Picture the transformation. A wide, bright spiral, its arms sweeping through a dense gathering of young galaxies. Then, over billions of years, the arms fade as new stars stop forming. The disk puffs up with each collision. The color shifts from blue to gold to red. Finally, a vast, smooth, quiet sphere of ancient stars, sitting at the heart of a cluster, with no sign that it was ever a wheel at all. If that is right, then the big wheel's snapshot is precious in a specific way. It captured a fleeting state, a galaxy in its brief spiral prime, and that state is exactly the one that challenged the model. Only a telescope looking that far back could ever have seen it. What the early universe built quickly, it also enriched quickly, with the elements that make planets possible. And that raises a question that reaches well past astronomy. Planets need heavy elements. Heavy elements come from stars, and if the early universe made stars fast, it may have made worlds far sooner than anyone assumed. Earth formed about 4.5 billion years ago, roughly 9 billion years after the beginning. Our star, and the cloud that became our planets, inherited heavy elements from generations of earlier stars. For a long time, the standard assumption held that rocky planets required a universe that had been enriching itself for many billions of years, and that early galaxies were too poor in heavy elements to build them. The chemical measurements described earlier tonight complicate that assumption. Several galaxies at 1 billion years and earlier show heavy element abundances that older models reserved for far later eras. Some show dust, which requires the same elements. If those galaxies could form dust, they could, in principle, form the small rocky grains that stick together and grow into planets. The raw materials were present earlier than expected. Here is the honest boundary. No planet has ever been detected in a galaxy beyond our own, let alone in the early universe. Planet detection depends on measuring tiny effects in the light of individual stars, which is impossible at those distances. What astronomers can do is measure the ingredients, and the ingredients appear to have been available. Whether planets actually formed is an inference from chemistry, and it should be held as a reasonable possibility rather than a finding. There is supporting evidence closer to home. Within our own galaxy, astronomers have found planets orbiting stars that formed very early in the galaxy's history. Stars that are poor in heavy elements compared with our own, but that still manage to build worlds. One such system, a pair of planets around an ancient star, has an estimated age of around 11 billion years, which places its formation within the first few billion years after the beginning. That is confirmed observation inside our galaxy, and it shows that planet formation does not require a heavily enriched environment. Consider the implication carefully. If planets could form around 11 billion years ago in our own galaxy, and if early galaxies elsewhere were enriched even faster, then planets may have existed in the universe for most of its history. Some of the earliest could have formed in disks like the Big Wheel, around stars born in its spiral arms, in an era when the universe was just learning to build galaxies at all. None of this says anything about life, and the restraint matters. A rocky planet is not a living one. The conditions for life involve far more than the presence of heavy elements, and early planets would have faced environments with intense radiation, frequent nearby stellar explosions, and rapid change. But the timeline for the first possible worlds has moved, quietly, in the same direction as the timeline for galaxies. Earlier, picture a planet forming in the Big Wheel, 2 billion years after the beginning, around a star in one of its curling arms. Rocky, young, orbiting a star that has itself only just formed, in a galaxy that should not have existed yet. Then follow its history forward, nearly 12 billion years of orbits. If it survived its galaxy's transformation, it is older than Earth by a margin wider than the entire age of our own world. Out there tonight, in the direction of a distant quasar, its light is still traveling. And so is the light of every other star you can see, each one a message from a different moment in the past. Everything covered tonight rests on one fact so familiar that it is easy to forget. Looking out into space is looking back into time. Light moves at a fixed speed, about 186,000 miles every second. That is fast enough to circle Earth several times in the blink of an eye, and yet the universe is so vast that light takes years, centuries, and billions of years to cross it. When you see a star, you are seeing light that left it some time ago. You are seeing the star as it was, not as it is. The sky is a collection of moments, each one from a different point in the past. Consider the closest examples. Light from the nearest star to our own takes a little over 4 years to arrive, so its image in the sky is 4 years old. Light from the bright stars that make up familiar constellations is often hundreds or thousands of years old. If one of those stars had ended its life a century ago, the news would still be on its way, and it would still be shining in the sky tonight. Now stretch that further. The faint band of light that stretches across the sky on a dark night is the disk of our own galaxy, seen edge-on from inside it, and its light is tens of thousands of years old. The nearest large galaxy beyond our own appears as a faint smudge to the unaided eye from a dark location, and its light left 2.5 million years ago, before modern humans existed. It is the most distant thing a human eye can see without help, and it is a message from the age of the earliest stone tools. The Big Wheel takes this to its limit. Its light left almost 12 billion years ago, Nothing about the galaxy as it exists now has reached us, and nothing will for billions of years more. What this telescope captured is a moment from the deep past, preserved in light, arriving only now. There is a strange and calming consequence in all this. The universe cannot be seen as it is. It can only be seen as it was, layer upon layer, with more distant layers older than nearer ones. The distant universe is a fossil record made of light, and telescopes are the tools for reading it. Every deep field is a core sample through time. This also means the early universe is not gone. It is still arriving. Light from galaxies at 1 billion years is reaching Earth tonight, right now, in the same way the big wheel's light did. Some of it is landing on the mirrors of telescopes. Some of it is landing on the roof over your head. Somewhere in the faint glow of the night sky, mixed with everything nearer, there are photons that began their journey before the universe had built its first spiral. Picture standing outside on a clear night. Above you, stars whose light is decades old. Behind them, a galaxy whose light is millions of years old. Behind that, invisible to the eye, but present all the same, the light of the first galaxies, still traveling, still arriving, passing quietly through the air around you. The universe wrote its history in light and sent it in every direction. Tonight, a little of that history has been read aloud. There is one more thing to say before the reading ends. It began with a photograph that should not have been possible, and it ends here, in a quiet room, with the light of that photograph still arriving. Take the long view one last time. A single spiral galaxy, seen 2 billion years after the beginning, forced astronomers to look again at how fast the universe can build order. A census of hundreds of ancient galaxies showed it was not alone. Radio dishes in a desert found rotation at 5% of cosmic time. A twin of our own galaxy appeared at 1 billion years. A bar of stars, a retired galaxy, a heavy black hole, a fog lifting, and a first generation of stars still hiding just beyond reach. Each one moved the clock earlier. Then the story turned toward explanations. Invisible halos forming early, rivers of cold gas, breaks that failed to engage in time, dust that recorded generations of dead stars, collisions that rebuilt disks instead of breaking them, a crowded neighborhood that may have fed the big wheel rather than disturbing it, simulations being rerun, one setting at a time, to find the rule that produces both the big wheel and the galaxy overhead tonight. And finally, the story came home. Our own galaxy began building a disk within the first billion years. Our sky is a map of time. Planets may have formed far earlier than anyone assumed. The framework of the universe stands, while one floor of it is being rewired. Here is the honest ledger. Confirmed. Early disks exist, they are common, and the old timeline was too slow. Under test, several candidate explanations, none yet proven. Unknown. The true nature of the little red dots, the identity of the first stars, and what the earliest galaxies looked like before disks formed. Open questions like these are not failures. They are the reason there will be more to learn next year than there was this year. Consider what has not changed. The stars above you tonight are exactly where they were before this story began. The galaxy carrying you around its center is still turning at the same steady pace, completing one orbit every 200 million years or so. Nothing tonight has made the universe stranger. It has only shown that the universe was already stranger and faster and more capable of order than anyone had noticed until a few years ago. Picture the big wheel one last time, wide and calm and spinning in a crowded young universe, its arms full of new stars, its light setting out on a journey that would take almost 12 billion years. Somewhere along that journey, our own galaxy settled, our star formed, Earth cooled, life began, and eventually someone built a telescope, pointed it at a quasar, and caught the wheel in the corner of the frame. The light is still arriving. It will keep arriving long after tonight, and if your eyes have closed by now, that is exactly as it should be. The universe kept building itself long before anyone watched. It does not need you awake to continue. So let the story rest here. Let the wheel keep turning in the dark, and let yourself drift, carried around the center of a galaxy that grew up early, under a sky that is always quietly arriving. Sleep well.